Hello there, and welcome to Life Beyond Seen, where curiosity settles in beside you, and science moves at a gentle pace, so your thoughts can slow down after the weight of the day. Tonight we're setting our course toward one of the most unreachable places on the planet, a place so remote that even the machines built to explore the deep hesitate at its threshold. The Japan Trench is not simply a point on the map or a darker shade of blue on an ocean chart. It is a place defined by distance, pressure, and limits that push back against every attempt we've made to understand them. And before we drift down toward that uneasy frontier, I'd love to hear where you're listening from and what time it is in your corner of the world right now. Strange, isn't it? How a place as quiet and unused to human presence as the bottom of the ocean can share a moment with you wherever you are. If this journey helps you unwind, or if you find the slow pace comforting, you'd be doing this little space a kindness by liking the video or maybe subscribing. It helps this calm shoreline reach others who might be looking for it without quite knowing they are. So take a breath, settle in, and let your thoughts loosen a little as we begin. When most of us picture the ocean, we imagine something familiar. Waves meeting the shore, maybe the surface rolling under a bit of wind, or the kind of shallows you can wade into without much concern. Even stories about the deep sea tend to come from documentaries that bring lights and cameras into that world, giving the impression that you could travel far enough, dive long enough, and eventually reach the bottom given the right equipment. But that picture only fits the uppermost layers. The Japan Trench is not part of that world. It belongs to a realm where normal expectations stop working long before you arrive. It sits east of Japan's coast, following the collision of tectonic plates that slowly drag one part of the Earth beneath another. The result is a long, steep drop into darkness, a place shaped by forces that don't care about our curiosity or our confidence. For as long as people have studied the ocean, there has been a quiet understanding that some places are more willing to be explored than others. The Japan Trench has never been one of them. Imagine starting at the surface on a calm morning. You can hear things up here, waves, wind, the occasional gull if you're close enough to land. Sunlight still has meaning. Colours still work the way you expect them to. But as you begin to sink, the water thickens around you. A few meters is nothing. 100 meters is still the world of divers and bright fish. By the time you reach 1,000 meters, light becomes a distant rumour, and sound changes shape. And yet this is barely the beginning. The Japan Trench drops more than 8,000 meters down. That distance isn't just depth, it's a change in the rules governing almost everything we understand. Pressure doesn't build slowly, it rises like an argument that never gives you time to answer. Every additional meter adds weight, and soon that weight becomes something beyond comparison. If you tried to describe it as the mass of buildings or mountains pressing inward, it still wouldn't match the reality of what exists down there. This is where exploration becomes less about curiosity and more about limitation. Humans were never meant to be exposed to this kind of environment. Our bodies, built for relative stability at the surface, would collapse instantly under the tremendous force waiting in the deep. This isn't an invitation to fear, only a reminder that some environments require more than determination. They require materials and engineering built for punishment far beyond what we see in daily life. Even the best submersibles in the world, the ones designed with reinforced titanium spheres and windows thick enough to support small structures on land, feel the strain of those depths. Every weld, every bolt, every layer of hull is a small negotiation with a place that doesn't give out second chances. People often imagine that if we can build rockets, space stations, and telescopes that see galaxies forming billions of years ago, then reaching the bottom of the ocean should be simple. After all, outer space has no pressure. The deep sea has too much. Space is cold, but at least it doesn't squeeze. The ocean does both. In fact, exploration beneath the sea is in many ways more difficult than travelling into space. A spacecraft must withstand the vacuum and maintain internal stability, but a deep-sea craft must resist an external force so powerful that a small structural mistake becomes catastrophic long before anyone realizes something is wrong. The Japan Trench sits far beyond what most vessels can endure. Even the ones built for extraordinary dives treat these depths as temporary visits rather than a place where we can linger. Technology has pushed forward, yes, but always cautiously. Engineers test new materials, design spherical hulls to spread out the force evenly, and monitor every part of a submersible for the slightest hint of weakness. But the deeper you go, the more everything fights against the idea of survival. The pressure at the bottom of the Japan Trench is more than 1,000 times the pressure at sea level. It's enough to crush metal that looks sturdy in every other context. It's enough to make electronics behave unpredictably, cables stiffen or snap, and seals that work perfectly well at moderate depths fail without warning. Exploration here isn't just hard. It pushes into a realm where the smallest oversight can end the mission within seconds. Even if you overcame the pressure, there's another challenge. The deep sea is cold in a way that drains energy from equipment continuously. Temperatures hover near freezing, which affects batteries, wiring, and mechanical systems that don't appreciate being pushed to their limits, while also losing heat as fast as they generate it. And of course, there is the darkness. Not the kind you experience in a room with the lights off, but a deeper kind, one that does not hold reflections or edges. This darkness hides the landscape, confuses cameras, and makes every movement uncertain. Floodlights help for a moment, but their reach is short, and all that lies outside their beams remains unreadable. Navigation becomes a guessing game unless you have instruments designed specifically to work without visual feedback. Yet despite all these obstacles, people have reached similar depths in other places. The Mariana Trench, for example, has been visited multiple times. So why is the Japan Trench more difficult? Part of the answer lies in geography. It runs parallel to Japan's eastern coastline and is tied closely to intense seismic activity. The tectonic plates that form this trench are active, constantly shifting, grinding, and adjusting. This makes the seafloor unstable in ways that complicate exploration. Landslides, collapses, and sudden changes in the terrain can disturb the deep environment, making it unpredictable for autonomous vehicles and submersibles alike. Instruments that rely on smooth communication between sensors and remote operators sometimes struggle to maintain stable connections in these conditions. Cables snag, signals distort, and the always present pressure amplifies the consequences. There is also the question of distance. While some parts of the trench are accessible enough for research vessels, others require longer travel times, more fuel, and more robust planning. Every moment spent above the trench carries risk. Weather systems move quickly in this region. Storms form without giving much notice. Waves can become rough enough to make deployments unsafe. Even lowering a submersible into the water requires calm conditions, and the Pacific doesn't always offer those when you need them. Missions are delayed for days or weeks, and sometimes cancelled altogether. The ocean decides when you can try again. Deep-sea exploration also depends on retrieving the equipment after the dive. A remotely operated vehicle or autonomous craft may descend into the trench, but it must also return. Surviving the pressure on the way down is only half the battle. The ascent is equally demanding, and if anything goes wrong, there is no simple recovery method. A malfunctioning craft might remain on the seafloor indefinitely, lost to pressure, darkness, and the unknown terrain below. This risk is not theoretical. Several expeditions over the decades have lost instruments in deep trenches, some swallowed by the landscape, others simply crushed beyond retrieval. The Japan Trench has a long history of reminding researchers that access is not guaranteed. Even reaching the depth is only the beginning of understanding it. The seafloor contains slopes, ridges, canyons, and unstable sediment that behave differently under pressure. Touching the floor can release clouds of particles that obscure visibility for hours. Moving too quickly can disturb the environment and cause mechanical strain. Staying still can be just as dangerous if unexpected shifts in the seafloor occur. We tend to imagine the ocean floor as a quiet, unmoving surface, but in trenches formed by subduction zones, the ground can be active in ways we cannot easily measure or predict. And then there is the human factor. Not fear or hesitation, but the practical realities of operating complex equipment in remote conditions. Crews spend long hours on research ships, monitoring instruments, calibrating sensors, and preparing for dives that may or may not be possible, depending on the morning weather. People become tired, equipment needs maintenance, plans shift constantly. Every attempt to explore the trench requires coordination of specialists, engineers, navigators, and scientists who must work together through unpredictable circumstances. All of this shapes how often we can visit, how long we can stay, and how much we can safely learn before returning to the surface. The Japan Trench remains one of the least explored parts of the ocean, not because we lack interest, but because each barrier reinforces the others. The pressure demands engineering at the edges of what materials can handle. The cold challenges energy systems. The darkness complicates navigation. The depth tests communication. The geography introduces instability. And the ocean itself guards access with weather that changes faster than plans can adapt. Each factor alone is manageable. Together they push the trench out of reach more often than they allow a successful dive. And yet people continue trying. Not with recklessness, but with patience. Every expedition teaches something about what is possible and what needs improvement. New materials are tested. Better imaging techniques are developed. Autonomous vehicles grow more capable. The Japan Trench may resist complete exploration, but each attempt brings us a little closer to understanding why it is so difficult to reach, and a little closer to respecting the environment that shapes its challenges. This is where our journey begins, not with an ending or a summary, but with the understanding that reaching one of the deepest places on Earth means confronting limits we rarely think about in daily life. As we continue downward, the landscape will shift again, and the challenges of the deep will open into new questions about what exists in the dark and why we can only access it for brief moments at a time. There is a point beneath the surface where the ocean begins to lose the memory of daylight. It does not happen suddenly. There is no clear boundary or visible marker. It's more like entering a room where someone is slowly dimming the lights. Not enough for you to notice at first, just enough for the world around you to take on a different quality. Up above, sunlight moves through the water in scattered beams that dance and shift with the waves. But as you drift farther down, those beams begin to break apart. They stretch, weaken, and eventually fade until the colour you've known all your life no longer means the same thing. The ocean at this depth no longer reflects the world above. It begins to follow its own rules. Most of us have only ever experienced darkness as something temporary. A hallway light flicks off, a lamp fails, or night settles in before you've turned on a switch. Even then, there is usually a window, a street lamp outside, or some familiar outline that lets you know where you are. The ocean doesn't offer that. When you descend below the layer where sunlight can travel, you step into an environment that does not adjust to your presence. It doesn't try to meet you halfway. It simply continues being itself, and that self is shaped by the slow disappearance of light that once defined the surface world. Around 200 meters down, the brightness changes into something muted. You could still read shapes if you were there, though it would be more difficult. Down a bit farther at 300 or 400 meters, colours begin to shift. Reds vanish first, then oranges. By the time you reach 1,000 meters, what remains is a world that recognizes only blues and greens, and even those fade quickly. Eventually the water becomes a place without colour altogether. Not black exactly, because black implies a surface reflecting nothing. This is something different. It's an environment where light doesn't travel far enough for your eyes to interpret anything, even if you could stand there with a flashlight in hand. This is the realm where the ocean begins to forget the sun. Life continues, of course, but it does so without relying on the cues most animals depend on at the surface. Plants cannot live here because they require sunlight to create energy. Coral reefs, seaweed, and the familiar ecosystems of the shallows get left behind long before this point. Everything that remains has learned to live in a world where illumination is a rare visitor rather than a constant presence. Some creatures create their own light through chemical reactions. Others move quietly through the dark, relying on senses that function without relying on vision. It's a world built from adaptation rather than familiarity. The Japan Trench, with its steep descent and unforgiving conditions, begins to show its character long before you reach its deepest points. As the light fades, the shape of the water changes. The pressure increases more aggressively. Sound begins to travel differently, moving faster and more clearly in some cases, yet strangely muted in others. If you could stand still and listen, you might hear distant groans from shifting tectonic plates, or the quiet movement of unseen animals. You might hear nothing at all. Silence and sound blend differently here, depending on how far vibrations can travel before they are swallowed by the water. A submersible entering this region must already be strong enough to handle pressures that would crush anything not specifically designed for the task. The water around it squeezes inward with growing insistence. Engineers design these vessels with thick, rounded hulls because flat surfaces would buckle under the strain. Even the viewing ports made of specialized glass are crafted to withstand thousands of pounds of pressure per square inch. At this stage of the descent, every piece of equipment is still functioning well, but the gradual change in temperature, density, and darkness begins to test the limits of sensors and lights. Illumination becomes a practical question, not just for visibility but for survival. Bright lights attract attention, and attention is not always safe. Some deep-sea animals are drawn to artificial light because it disrupts their usual conditions. They approach to investigate, perhaps out of curiosity or confusion. Others avoid it as if it signals danger. A research vessel must be cautious about flooding the area with too much brightness. The lights are usually narrow beams designed to illuminate only what needs to be seen, allowing the surrounding dark to remain undisturbed. Too broad a light could reflect off particles or plankton, creating a glowing cloud that makes navigation harder. Every meter downward strips away something familiar. Even temperature becomes a factor. Near the surface, sunlight warms the upper layers of the ocean, creating regions where swimmers, divers, and sea creatures can move comfortably. But down below, the warmth dissipates. Gradually at first, then suddenly. The water temperature drops to near freezing, a steady cold that leaches heat from anything immersed in it. For marine animals, this is part of their normal environment. For machinery built by humans, it is another source of stress. Cold affects how batteries hold power, how cables remain flexible, and how instruments respond to commands. As the ocean forgets the sun, it becomes a place shaped entirely by survival and patience. The creatures that live here move with caution. Their bodies conserve energy because food is rare. Many rely on falling material from the surface, tiny particles, bits of organic matter, even the occasional larger piece of debris drifting downward. This slow rain of nutrients is sometimes called marine snow, a simple term for something that supports an entire network of life in the dark. It falls constantly, though unevenly, and whatever reaches the deeper layers is often all that sustains the organisms living there. While the Japan Trench itself continues far deeper, this region where light finally fails marks a turning point. Above this depth, explorers can still rely on cameras, floodlights, sonar, and visual interpretation. Once the light is gone, everything must operate through instruments designed to function without the support of visual cues. Sonar becomes more important. Pressure-resistant imaging tools become essential. Navigation must account for the fact that the seafloor may not be visible until the vessel is very close. Even the water's movement shifts. Currents in the deep are slower, quieter, and less predictable. They can push a vehicle off course without giving any hint through visual signs. People often imagine that darkness itself is the obstacle, but in truth, darkness is merely a symptom of something larger. The loss of sunlight means the ocean is no longer part of the world we know at the surface. It becomes a place ruled by pressure, chemistry, and slow-moving life forms that have no interest in rising to greet us. Exploration here requires tools that do not behave the way human senses do. The vessel becomes the explorer, not the human inside it. Sensors act as extensions of awareness. Sonar serves as a kind of hearing. Pressure gauges act like touch. Cameras provide sight only when aided by artificial light, and even then the environment reacts differently to that illumination. The ocean does not reveal itself easily. This gradual transition away from sunlight also signals the beginning of real constraint. Not in a philosophical way, but in an engineering sense. Every system that keeps a submersible functioning has to operate within a narrow range of values, yet the deep sea pushes against those values constantly. The hull expands and contracts microscopically under the changing conditions. Lights become less effective. Cameras require stable temperature regulation. Cables stiffen. Electronic circuits behave differently. All of this begins during the descent toward the Japan Trench, and it continues to intensify as the depth increases. Some people imagine that because we have explored other deep locations like the Mariana Trench, that the challenges must be similar everywhere. But the shape of the seafloor, the slope of the descent, the surrounding currents, and the water's clarity all change depending on the trench. The Japan Trench has steep sides, unstable geology, and unique temperature gradients that complicate the descent. The trench is also located near regions of seismic activity, meaning the deep environment can shift unexpectedly. Sensors that rely on stable conditions may misread data. Instruments carefully calibrated at the surface must adapt to a changing landscape that cannot be predicted fully. Navigation becomes a thoughtful process. Research teams monitor every signal, every pressure reading, every noise from the submersible. Communication between the surface vessel and the submersible often weakens as the descent continues. The thick water and increasing distance limit how quickly information can travel. Commands take longer to send. Responses move more slowly. Delays become part of the operation. If something begins to malfunction, the team must evaluate whether it's safe to proceed. They cannot rely on direct feedback the way they would on land or in shallow water. As the ocean grows darker, animals adapted to this region sometimes drift into view. They are not aggressive, merely present. Some move with slow, steady motions, conserving energy. Others pulse through the water using bioluminescence as a kind of signalling system. Their light isn't bright enough to illuminate the surroundings, but it glows just long enough to reveal shapes that come and go without warning. A submersible that shines a light on them will see reflections on their bodies for a moment, before they disappear again into the distance. They are not hiding. They simply belong to an environment that absorbs light faster than it can travel. This portion of the descent is quiet, not because nothing is happening, but because everything occurring here happens slowly. The pressure continues building. The temperature continues falling. The darkness becomes absolute. The water's density increases to the point where even sound travels differently. A submersible might hear distant movements that cannot be traced, echoes that hint at geological activity or unseen marine life. The trench region is known for its seismic unpredictability, and sound carries fragments of that activity through the water, long before anything could be observed visually. Even though human eyes cannot see in this darkness, the absence of light reveals something else. It clarifies just how much of the ocean is inaccessible to us without technology. The ocean begins to feel less like a familiar place, and more like a vast interior world with its own rules, and the Japan Trench amplifies this effect with every meter descended. The ocean forgets the sun not by rejecting it, but by existing in a state where light no longer plays a meaningful role. Everything here is shaped by pressure, chemistry, and the slow movements of water that have followed the same patterns for thousands of years. Exploring this region prepares the vessel and its crew for what lies deeper. The ocean is patient, but it does not compromise. As the descent continues, the challenges will accumulate, pressure will intensify, the temperature will remain unforgiving, equipment will be pushed to the limits of its design, and the darkness, now complete, will become the environment in which all systems must perform without error. From here on, the Japan Trench becomes more than a distant geographical feature. It becomes a test of endurance, not for the humans watching their screens, but for the technology that allows them to witness what lies far beyond the reach of sunlight. The farther you move from the surface, the more the water around you begins to behave like something you've never really encountered before. At first, it feels no different from the pressure you might experience while swimming or diving close to shore. A little heaviness around your ears, a mild squeeze that disappears the moment you rise again. But that sensation barely hints at what pressure becomes as the depth increases. The ocean doesn't add weight gently. It compounds it layer upon layer until the water itself becomes a force that seems determined to press inward with everything it has. This isn't an exaggeration. It is the reality of descending into the Japan Trench, where the weight of an entire world gathers around you and refuses to let you forget where you are. Pressure underwater doesn't behave the way most people imagine. It doesn't push only from above. It comes from every direction at once, surrounding anything caught within it. At 10 meters down, the pressure is already twice what it is at the surface. That's enough to make your ears ring if you descend too quickly. But the numbers don't grow in a linear way that feels manageable. By the time you reach 100 meters, the pressure is equal to 10 times what your body normally handles. At 1,000 meters, it's already 50 times greater, and the bottom of the Japan Trench is more than 8,000 meters down. The force there is immense, far beyond what bones, lungs, or skin were designed to withstand. Humans can't even consider being exposed to it directly. We rely on machines to survive the journey, and those machines must be engineered with a level of precision that leaves little room for error. A submersible built to survive these depths is not shaped for comfort or appearance. It is shaped for survival. The hull must distribute force evenly, which is why the strongest deep-sea craft are spherical. A sphere handles pressure better than any other form because it spreads the load equally across its surface. Even then, the steel or titanium used to build it must be thick enough to resist compression. Imagine holding a small metal sphere in your hand and knowing that every square inch of it must endure tons of force without warping or cracking. Now imagine that sphere surrounded by absolute darkness, isolated from the rest of the world, and expected to perform flawlessly for hours at a time. That is what deep-sea explorers work with. It's not bravery alone that takes them downward, but the trust they place in materials that have been tested again and again under conditions designed to mimic what waits in places like the Japan Trench. Pressure at these depths behaves in a way that borders on hostile. It isn't malicious, of course, but it leaves no margin for miscalculation. A small crack in the hull would widen instantly. A weak joint would give way without warning. Any flaw, even one nearly impossible to detect, can become catastrophic long before the crew has time to react. That's why deep-sea vessels are built slowly and inspected constantly. Every weld, every bolt, every seal is checked, revised and checked again. Engineers simulate pressure using large chambers that replicate the weight of the deep ocean. They force the materials to endure stress far beyond ordinary conditions. Only after a vessel passes those tests repeatedly do designers consider it ready for a real descent. Even with all that preparation, the ocean adds complications that cannot be fully replicated in a laboratory. Temperature plays a role. The cold water near the trench floor is close to freezing, which affects how metal behaves. Many materials become more brittle when exposed to such low temperatures. Electronics slow down, batteries lose efficiency, lubricants thicken or separate. A hull under pressure may respond differently when chilled to near 0 degrees Celsius. This combination of pressure and cold is part of why deep-sea exploration is so challenging. You're not designing a machine for a single extreme environment. You're designing it for two extremes that work together to test every component at once. Inside the submersible, the experience of pressure is not something the human body directly feels. The hull holds it back, keeping the interior at normal atmospheric conditions, but the knowledge of what lies beyond the metal walls remains. Explorers often describe the descent as both peaceful and unnerving. Peaceful because the ocean is quiet, unnerving because the silence is heavy with the weight around them. Every sound inside the vessel matters. A simple creak, which might mean nothing at shallow depths, becomes something you notice more closely down here. Engineers design the craft to make certain sounds so that nothing comes unexpectedly. A small groan in the hull can be normal as the material adjusts to the external force, but any unfamiliar noise is reason for immediate attention. The more pressure increases, the more carefully everyone listens. Pressure also changes how tools function. At the surface, a robotic arm can move smoothly and reliably. In the deep sea, that same arm must push against water so dense it might as well be moving through syrup. Hydraulic systems must work harder. Motors take on more strain. Joints and hinges must be sealed tightly to prevent water intrusion. Even the cables that connect external instruments to the rest of the craft are engineered with layers of protection. If water seeps into a connection, it can short out a system instantly. Redundancies are built into the design, but they are not limitless. A single failure can cascade into multiple problems if not addressed quickly. Every expedition that enters a trench must take these variables into account. Teams rehearse procedures for emergencies. They review how to respond if a system loses power or if communication with the surface weakens. They rehearse how to abort the descent, how to begin the ascent, and how to ensure the vessel rises safely. Unlike space travel, where an emergency often requires complicated maneuvers, deep-sea craft rely on buoyancy systems that can bring them upward with minimal effort. Still, those systems must function under extreme pressure. Release mechanisms must not jam. Backup flotation devices must deploy correctly. A small malfunction at 8,000 meters down is not comparable to one near the surface. Up here, a diver could swim or be pulled to safety. Down there is no direct intervention. Everything depends on the vessel. Pressure also affects the seafloor itself. The deeper you go, the more compacted the sediment becomes. But in trenches like the one off Japan, the ground is not smooth or predictable. Subduction zones, where one tectonic plate slides beneath another, create a jagged, shifting landscape. Some areas are covered in soft sediment that can cloud the water instantly if disturbed. Other areas are harder, fractured by seismic activity. Movements in the Earth's crust create vibrations that travel through the water, sometimes audible inside the submersible. These movements may be small, but combined with the surrounding pressure, they reinforce how unforgiving the environment is. Pressure shapes life in this region as well. Any organism that lives near the trench floor must be adapted to conditions that would crush most animals. Many deep-sea creatures have bodies without air-filled cavities. Some lack rigid bones altogether. Their structures are flexible, allowing them to withstand the constant external force. They are not simply surviving pressure, they are built for it. Their cells contain chemical balances that prevent collapse. Their bodies maintain shapes that function efficiently, regardless of the surrounding force. Life here is not fragile, it is specialized. Technology, however, does not adapt as naturally. Even the most advanced machines struggle against the depth. Pressure-resistant housings for cameras and sensors must be thick enough to prevent implosion, but also transparent or conductive enough to allow them to perform their tasks. Lights must be contained within protective casings that won't crack. Sonar systems must send and receive pulses through dense water that changes how sound travels. Every piece of equipment brought into the deep must function in a place where pressure constantly attempts to deform or disable it. There is also the question of time. The longer a submersible stays at extreme depths, the more the pressure works on it. Materials that can endure short exposure might weaken over hours. The hull remains strong, but joints and seals experience slow fatigue. Engineers know this and design missions with strict time limits. Explorers descend, gather data, and return without overstaying. They do not linger longer than necessary, not because they lack curiosity, but because they respect the endurance limits of the vessel keeping them alive. Pressure behaves like an invisible companion during the entire journey. It doesn't announce itself, but it is always present. It presses against the hull from every angle, reminding everyone on board how far they are from the surface. This constant weight becomes a defining part of the experience. Not frightening, but sobering. It encourages caution. It demands attention to detail. It explains why missions to the Japan Trench require equipment tested beyond ordinary standards, and why even the most experienced teams treat each descent with humility. People sometimes imagine that if a submarine can handle the pressure at one deep location, it can handle the pressure everywhere. But trenches have unique challenges. The Japan Trench is not the deepest point in the ocean, but the environment around it makes exploration complex. The steep walls, the seismic activity, the cold, the shifting currents, all of these combine with the immense pressure to create a place where exploration must be planned carefully and executed with precision. No matter how advanced technology becomes, pressure will always remain a fundamental barrier. It is not something we can eliminate, only endure. As you travel deeper, the pressure doesn't just build, it reshapes how everything behaves. Water that feels fluid at the surface becomes dense enough to slow down motion dramatically. Materials that seem strong on land become vulnerable. Systems that work easily in a lab must fight against conditions they were never originally meant to encounter. Everything must be rethought, redesigned, and reinforced. The deeper you go into the Japan Trench, the more apparent it becomes that pressure is the dominant force in this environment. It is the reason so few missions reach these depths. It is the force that keeps this place so rarely visited. It is what separates the surface world from the one that continues far below, waiting in darkness and cold. And as the descent continues, pressure becomes only one of several challenges waiting ahead, each building upon the last to shape a world that does not yield easily to exploration. Every attempt to understand the deep ocean begins with the machines we rely on to reach it, because without them the Japan Trench would remain completely out of reach. These machines are not built for comfort or style. They are built for survival and endurance, created specifically to do what the human body cannot. But even the strongest designs face limits, and those limits come into sharp focus as they approach depths that push engineering toward a breaking point. Pressure, temperature, darkness, and distance all work together as if they were trying to test how far we can stretch our understanding of materials and mechanics before something gives way. A submersible, no matter how advanced, is still a compromise between safety and capability. Engineers start with the basic question of shape. The deeper the dive, the more essential it becomes to use a form that distributes stress evenly. That is why the most pressure-resistant craft are spherical at their core. A sphere is the shape least likely to collapse under the crushing force of the deep ocean. But building a perfect sphere that can hold humans safely is complicated. It requires thick walls made from materials strong enough to withstand compression, far beyond what most structures on land ever experience. Titanium is often chosen because it resists corrosion and compressive stress better than many metals, but even titanium has limits at extreme depths. Engineers must calculate every millimetre of thickness, knowing that if they misjudge even slightly, the result could be catastrophic. Craft designed for the Japan Trench also face the challenge of navigating a landscape that offers almost no visual cues. Equipment must compensate for the lack of light, which means placing powerful lamps on the exterior. Yet those lamps cannot be too bright or too broad in their reach, because excessive illumination can scatter in the water and reduce visibility further. The housings around these lights must resist the same pressure as the hull. Glass, which we think of as brittle on land, becomes part of a reinforced casing designed to hold firm under thousands of pounds of force per square inch. Engineers use specialised materials that behave more like thick, transparent armour than anything you'd expect to find in a typical lens or window. Then there are the robotic arms, sampling tools, cameras, sonar devices, and communication systems attached to the vessel. Each of these must function flawlessly at depths where the environment does not tolerate mechanical hesitation. A robotic arm, for instance, must move smoothly while pushing against dense water. Its joints must be sealed tightly so that no water infiltrates the interior. If a single seal fails, the arm becomes useless. The pressure will force water into any opening, flooding the mechanism instantly. Engineers must create seals that hold under constant stress. They test them repeatedly under simulated conditions, but real ocean pressure is not always uniform. It shifts slightly with currents, temperature changes, and the subtle movement of the craft itself. Every shift influences how a seal behaves. Electronics present another challenge. At the surface, you can place a circuit board inside a lightweight casing and expect it to function without trouble. At depth, that same casing must be thick enough to protect the board from crushing forces. But building thicker casings creates new problems. Electronics generate heat as they operate. On land, that heat is usually manageable, but in a deep-sea vessel surrounded by freezing water and isolated behind pressure-resistant housings, heat becomes harder to dissipate. If the electronics overheat, they malfunction. Engineers must balance insulation with cooling methods that do not allow water intrusion. They use thermal conduction plates, pressure-proofed housings, and insulation systems designed to manage heat without compromising structural integrity. One of the most significant challenges for deep-sea machines is the simple act of maintaining communication with the surface. Radio waves do not travel well underwater. They weaken almost immediately. That leaves two main options: acoustic communication and physical cables. Acoustic communication uses sound waves to relay information, but sound travels through the deep ocean in ways that defy easy prediction. Layers of water with different temperatures and densities bend sound at odd angles, creating distortions or delays that make precise control difficult. Physical cables, meanwhile, introduce their own complications. A tether stretching thousands of meters becomes vulnerable to currents, friction, entanglement, and tension changes. In a trench with steep walls, a cable can snag easily. If it catches on a rocky outcrop, the entire mission may end before it properly begins. Autonomous underwater vehicles, or AUVs, are designed to remove the need for direct control. They are programmed in advance with routes, tasks, and behaviours. Once deployed, they act independently until it is time to return to the surface. But these vehicles rely heavily on sensors to understand where they are. In shallow water, GPS can help. Deep underwater, GPS signals cannot reach. AUVs must navigate using sonar, inertial systems, and internal mapping tools that estimate position based on movement. This works well in open water, but a trench environment complicates things. The steep walls and jagged geography create a maze that confuses sonar reflections. AUVs must be programmed carefully so they do not drift into dangerous areas or collide with hidden features of the seafloor. The Japan Trench is notorious for its challenging terrain. Unlike the broad, sweeping plains of some deep-sea floors, this trench is shaped by tectonic forces that constantly change the environment. Landslides occur that alter the shape of the seafloor. Sediment drifts into new positions. Fault lines shift during seismic events, creating cracks or ridges where none existed before. Machines sent into this region must be prepared for sudden changes. If an AUV approaches what it believes is open water but actually faces a newly formed slope, its sensors may detect the obstacle too late. Engineers must design the craft to avoid sudden impacts, but even with careful planning, the trench remains an unpredictable environment. Pressure affects every part of a machine, but so does the ocean's salt content. Corrosion becomes a slow but steady threat. Metals that might last decades on land begin degrading quickly underwater. Protective coatings help, but they cannot stop corrosion entirely. Some components must be made from specialized alloys designed to resist salt water, while others require regular replacement after each mission. Even cables, often reinforced with layers of shielding, suffer wear from movement, friction, and exposure to the deep-sea environment. Buoyancy systems are another delicate part of the design. A deep-sea vessel must be heavy enough to sink, but buoyant enough to rise when needed. Engineers use syntactic foam, tiny glass spheres embedded in resin, to create flotation material capable of resisting extreme pressure. Ordinary foam would collapse instantly under deep-sea conditions. Syntactic foam, however, maintains its shape, but it is not invincible. At extreme depths, even this specialized material can deform slightly. If it deforms too much, the vessel may struggle to ascend. Engineers must carefully calculate how much flotation is needed, how much weight the craft can safely carry, and how the buoyancy will behave at depth. These calculations are precise because small misjudgments create significant risks. Batteries bring their own difficulties. A submersible cannot rely on solar power. It must carry all its energy with it. Batteries lose efficiency in cold temperatures, and the deep ocean remains consistently cold. Engineers compensate by using advanced battery designs and insulating them, but insulation can trap heat. Just as with electronics, a careful balance must be maintained. If the batteries become too cold, they lose power. If they become too hot, they fail. At extreme depths, where the craft cannot afford a sudden loss of power, maintaining stable battery temperature becomes a vital part of the mission. When scientists discuss the deep ocean, they sometimes compare it to outer space, but in many ways the ocean is harder to explore. A spacecraft faces vacuum and radiation, but it does not face crushing pressure. Deep-sea craft must endure enormous external force while keeping everything inside at a safe, stable pressure. If a spacecraft develops a small leak, astronauts can sometimes seal it. If a deep-sea vessel develops a leak, the pressure forces water inward so quickly that there is no time to react. The machine must be built well enough that nothing leaks in the first place. Tools designed to collect samples must also withstand the depth. A simple container that works well near the surface would collapse instantly at trench depths. Even the hinges on a sample box must be built from materials that resist deformation. If a hinge bends even slightly, the box may not close properly. If it does not close, pressure pushes water inside, destroying whatever sample the researchers hoped to collect. Collecting sediment requires suction tools that can operate under pressure. Collecting biological samples requires soft grip devices that do not harm the organism while still functioning in thick, cold water. Every tool must be redesigned for deep-sea use. What makes all this even more complicated is that machines built for the Japan Trench cannot simply be tested in real conditions until the final mission. Pressure chambers can simulate some conditions, but they cannot replicate the full combination of pressure, temperature, and geography simultaneously. Engineers must rely on models, simulations, and educated assumptions. They test components separately, but they cannot fully reproduce the environment those components will face. When a machine descends into the trench, it is entering an environment that still holds surprises, no matter how carefully the mission has been planned. Failures have happened. Some are minor, lights flickering, cameras fogging, sensors losing calibration. Others are more serious. Over the decades, more than one vehicle has been lost to depths where retrieval was not possible. Some imploded under pressure, leaving only fragments. Others became trapped, their tethers caught on unseen ridges or rocks. Autonomous vehicles have occasionally vanished without a trace, never returning to the surface. These losses remind scientists and engineers that even with modern advances, the ocean remains a place where technology faces limits not encountered anywhere else on Earth. But each failure teaches something. Engineers review every detail, learning what needs improvement. Materials are refined, seals are strengthened, battery systems are redesigned. sonar technology becomes more accurate. The machines built today reflect decades of gradual improvement born from difficult lessons. Still, there remains a point beyond which improvements struggle to help. Some depths simply push materials and mechanics close to their breaking points. The Japan Trench, with its complex geography and intense pressure, is one of those places. Deep-sea machines bend before they break. They bow slightly under pressure. They shift in ways that would not be noticeable at the surface. They adapt just enough to maintain integrity, but only within the limits engineers designed. If pushed too far, even the strongest craft would fail. That is why each descent must be measured, controlled, and monitored. The machines take on the burden of the deep so that the researchers inside or watching from above can witness a world otherwise unreachable. As these machines descend, every meter brings new demands. The ocean applies pressure with complete consistency. It does not adjust for curiosity. It does not soften because a mission is important. The machines must do all the adjusting themselves, responding to conditions that grow more intense as the journey continues, and each success reveals only a small part of the trench. The limits of the machines remain, shaping how much of this deep world we can explore at any given time. The farther a submersible moves into the depths surrounding the Japan Trench, the more the environment shifts into something that no longer resembles anything familiar at the surface. What begins as dimness transitions into a level of darkness that changes the meaning of visibility itself. It is not the temporary darkness you find when a power outage turns off the lights, or when you step into a basement without flipping a switch. This is a darkness created by the total absence of sunlight, a condition so complete that the space around you becomes a physical environment rather than simply a lack of brightness. Down here, darkness behaves like part of the landscape, shaping how machines operate, how animals move, and how explorers must think. Most people think of the deep ocean as dark simply because light cannot reach it. That's true, but the implications go far beyond not being able to see. Light doesn't just provide visibility. It defines boundaries, shapes distance, reveals surfaces, and gives structure to the world. Without it, the entire environment becomes a space where the usual cues do not apply. Even when a submersible uses its own lights, those beams extend only a short distance before fading into thick water that scatters the illumination. The light doesn't stretch smoothly outward the way it does in air. Instead, it hits particles suspended in the water, reflects unpredictably, and loses strength almost immediately. Even powerful lamps illuminate only a narrow cone directly in front of the vehicle. Everything outside that cone remains hidden. This has practical consequences. A pilot or operator cannot rely on visual information to understand the surroundings. The seafloor might be nearby or far away. A slope or rock formation might be directly ahead but invisible until the lights land on it at the last moment. The darkness creates uncertainty in every direction, and no amount of technology fully eliminates that uncertainty. Cameras help, but cameras need light. Sonar helps, but sonar requires interpreting echoes in a space where the geometry of the trench constantly changes. The combination of darkness and shifting terrain turns navigation into a slow, deliberate process. Even the appearance of the water changes in this depth. Instead of looking clear or blue, it takes on a thicker, almost physical quality. It absorbs light so efficiently that everything outside the beam seems to disappear completely. Objects do not fade gradually into the distance, they vanish abruptly. A rock formation 3 meters away might be visible, but another one 5 meters away might not reflect enough light to be noticed at all. This kind of darkness affects how operators judge distance. Something that looks close may actually be far away, depending on how the light interacts with the water at that moment. This is where the idea of darkness becoming a landscape becomes clear. When you cannot rely on vision, the environment becomes defined by what your instruments tell you, rather than by what your eyes can see. The seafloor becomes a pattern of sonar readings instead of a visible surface. The space around the craft becomes a series of measurements rather than observable surroundings. Every movement depends on interpreting this data correctly. A slight misreading could send the vessel too close to a slope or a rock outcrop. Because the trench is steep and irregular, this risk increases with depth. For the creatures living in this darkness, the absence of sunlight is normal. They do not rely on visual cues the way surface animals do. Some species have small or non-existent eyes, because seeing provides no advantage. Others produce faint bioluminescent glows, not to light their environment, but to communicate or attract prey. These glows are brief and localized, not bright enough to illuminate the space around them. They function more like signals than light sources. If a submersible's lights catch one of these creatures, the glow becomes visible for a moment before the animal drifts away and disappears again. The presence of bioluminescence reminds explorers that life continues even in extreme conditions, but it also complicates visibility. Sometimes small glowing organisms drift into the beam of the submersible's lights, scattering reflections and creating visual noise. This makes the darkness feel even more substantial, because it shows how many particles and organisms float unseen until illuminated. Every movement of the submersible disturbs the water slightly, sending these particles into motion. For a short time, the water ahead might sparkle faintly with tiny reflections before returning to its usual state. This reinforces the idea that the darkness isn't empty. It simply hides everything until light reveals it. Even with artificial lights, deep-sea explorers often describe the environment as though the darkness is leaning in around the vessel. The lights create a small bubble of visibility, but beyond that bubble, the water remains unaffected. No matter how bright the lamps are, the darkness absorbs more than it reveals. Engineers could attach brighter lights, but doing so introduces new issues. Bright lights require more power. More power creates more heat. More heat must be controlled carefully to prevent system failures, and extreme brightness can attract animals that react unpredictably. Most missions choose a balance between visibility and safety, rather than trying to overpower the environment. The limitations of visibility also affect how the submersible approaches the seafloor. When the craft nears the bottom, it must slow down considerably, because the darkness hides subtle changes in elevation. It is easy to descend too quickly in an area where the seafloor rises unexpectedly. For this reason, pilots rely heavily on sonar, but sonar provides an interpretation, not a picture. It tells you the distance to the nearest solid surface, but it does not show slope angles, textures, or obstacles in detail. A cautious approach is essential. The deeper the vessel goes, the more its team must rely on indirect information to understand what lies ahead. At these depths, darkness also influences how sound behaves. Without visual cues, sound becomes one of the main tools for sensing the environment, but sound travels differently underwater than it does in air. It moves faster and can bend through layers of water with different temperatures and densities. This means that a noise may seem to come from a direction that does not match its origin. The trench walls may reflect sound in ways that confuse interpretation. A creaking noise from the hull might sound amplified, while distant seismic vibrations may seem closer than they are. The darkness removes visual confirmation, so the team must trust their instruments and training. The absence of light also affects how time feels inside the submersible. Without windows showing anything but blackness, there is no external visual reference. It could be midday or midnight on the surface, but down here those distinctions disappear completely. The people inside the vessel rely on their clocks and communication with the support ship to maintain a sense of time. Missions are planned carefully so that every stage has a schedule, but the environment itself offers no cues. This sensation can make the darkness feel even more dominant, because it removes a sense of orientation that humans usually take for granted. Machines must operate with precision in this darkness, but even the best engineering cannot fully compensate for the lack of visual information. Cameras may record footage, but the footage often shows only small patches of illuminated terrain surrounded by nothingness. Researchers must interpret these images within the context of sonar data, pressure readings, and other instruments. Every frame of video becomes a puzzle. What is the scale of the object? How far away is the next formation? Is the sediment thick or thin? How steep is the slope outside the visible area? The darkness ensures that these questions cannot be answered with a single tool. Exploring the Japan Trench means understanding that darkness is not an obstacle to be defeated. It is a condition to be respected. No amount of technology removes it entirely, it can only be managed. The lights on a submersible allow a brief look into the surroundings, but they do not change the nature of the environment beyond their reach. The trench remains enveloped in a darkness that persists whether someone is there or not. The deeper the vessel goes, the more the darkness gains weight. Not physically, but through the way it influences perception and decision-making. When the surrounding world cannot be seen, the importance of every instrument reading increases. A slight change in sonar feedback, a small shift in depth, or a minor fluctuation in water temperature must be examined carefully. The darkness does not provide warnings. It does not reveal sudden drops, rising outcrops, or unexpected terrain changes unless illuminated at close range. The crew cannot assume anything. They must interpret every detail the instruments provide. This also affects how missions are designed. Researchers must decide which areas to explore and how close to the seafloor they can safely travel. They may choose to avoid certain slopes or geological features entirely because the darkness makes navigation too risky. Even when they gather valuable data, they often return to the surface with the understanding that large portions of the trench remain unseen simply because the darkness prevented safe exploration. For autonomous vehicles, the challenge is even greater. Without direct human input in real time, an AUV must make decisions based on its programming. If its sensors detect an obstacle too late, it cannot correct itself quickly enough. For this reason, AUVs must maintain safe distances from the seafloor. They map the environment in broad strokes rather than detailed views. Their data is useful but limited by the fundamental issue of visibility. The darkness dictates how close they can approach and how much detail they can capture. Even when light reveals the terrain, the images often show only fragments: a piece of rocky wall, a patch of sediment, a cluster of small organisms. Almost everything else remains hidden. This partial visibility challenges researchers who want to understand the geology or biology of the trench. They must infer patterns based on incomplete information. The darkness guarantees that even well-planned missions produce more questions than answers. Down here, the darkness becomes an environment that defines everything else. It shapes how machines function, how animals live, and how scientists gather data. It forces slow movement, cautious planning, and constant monitoring. It limits the detail that can be observed and preserves the unknown across most of the trench. As the descent continues, this darkness blends with pressure, cold, and isolation to create a world that only offers narrow glimpses of itself at a time. Life in the deep ocean has to operate according to rules that are completely different from the ones we know near the surface. At the bottom of the Japan Trench, the pressure is overwhelming, the temperature is just above freezing, and the darkness is permanent. Yet despite these conditions, living organisms exist there. They do not simply survive, they function in ways that make sense only when you understand how different the environment is. These creatures are not fragile exceptions. They're examples of what evolution can accomplish when the requirements for survival push everything far away from anything familiar. Most animals we know depend on sunlight, either directly or through food chains that begin with photosynthesis. But sunlight does not reach the deep ocean. Plants cannot grow. The usual chain of energy is interrupted. Any life down here must find alternatives. In trenches like the one off Japan, some organisms rely on the slow descent of organic material from above. It may be small fragments from upper layer ecosystems, dead plankton, drifting tissue, or even larger carcasses that sink slowly through the water column. This material takes days or weeks to fall, gathering along slopes and valleys where animals can feed on it. The predictable part of their world is not the arrival of food, but its scarcity. They must be adapted to handle long periods with little energy intake and sudden opportunities when something substantial finally reaches them. Many deep-sea creatures have pliable bodies because rigid structures do not tolerate extreme pressure. Bones, air sacs, and hard shells collapse or crack if they contain spaces that air cannot compress further. Instead, these organisms have tissues filled with fluid that matches the pressure outside. Their internal and external pressures remain balanced. Cells maintain function because they contain proteins adapted to prevent distortion under intense force. This balance is not something surface organisms can achieve. Fish from shallow waters, for example, would not simply be crushed by pressure. Their biochemistry would fail long before any physical collapse occurred. The proteins in their cells would not fold correctly, and their metabolism would break down. Deep-sea animals are built in ways that make these failures impossible during their normal lives. One example of adaptation is seen in amphipods, small crustacean-like creatures that live in some of the deepest parts of the ocean. They appear delicate, yet their bodies are structured without gas-filled cavities. Instead of relying on calcium carbonate for their shells, which dissolves under high pressure and low pH, they use substances that do not break down easily. Even their membranes incorporate special molecules that preserve flexibility. This allows them to function under immense external force. They move efficiently in dense water and respond quickly to small changes in their surroundings. In an environment where energy conservation matters, these adaptations are critical. There are also snailfish found in various trenches, including locations near the Japan Trench's depth range. These fish look soft and almost gelatinous, but that softness is precisely what protects them. Their bones are reduced. Their muscles are suited for slow movement. They do not waste energy swimming quickly, because that would require more oxygen than they can efficiently extract from the cold, dense water. Their bodies contain compounds that help stabilize proteins under pressure. These compounds prevent their tissues from losing function when the pressure becomes too great for normal cellular structures. The delicate appearance of these fish hides the fact that their biology is reinforced for conditions that would destroy most other organisms. Other creatures rely on chemical energy rather than drifting organic matter. In some deep-sea environments, microorganisms use chemicals released from geological activity to produce energy. While the Japan Trench does not have the hydrothermal vent systems found in other regions, microbial life still thrives in sediment layers, breaking down material that sinks slowly from above. These microorganisms form the foundation of smaller ecosystems within the trench. They influence nutrient cycles, support other organisms, and play a role in shaping the biological processes that occur in the deep. One of the most striking aspects of life in trenches is how these organisms respond to sound. In shallow waters, many animals rely on visual cues. Down here, vision has limited value unless the organism produces its own light or reacts to the faint bioluminescence of others. Instead, vibration and pressure changes become essential. Some animals detect subtle movements in the water, sensing shifts that help them locate food or avoid threats. The Japan Trench environment produces natural vibrations from shifting sediments and seismic activity, and many organisms seem adapted to process these signals without becoming confused by constant background noise. Because food is limited, deep-sea animals often show slow metabolic rates. They take longer to grow, longer to reproduce, and longer to react to changes. This slow pace helps them conserve energy. A creature might only eat occasionally, but when it does, it stores resources efficiently. Reproduction is also shaped by the environment. Some species release eggs or larvae that drift through the water, spreading widely so that at least some reach favourable areas. Others rely on slow, direct reproduction within the same region, making sure that the young begin life already adapted to trench conditions. Some organisms demonstrate unusual feeding strategies. Sea cucumbers, Brittle stars and other bottom dwellers filter the sediment, extracting nutrients from the material that has settled over time. Scavengers move toward any new source of food, whether a large carcass or a sudden deposit of organic particles. These responses may seem simple, but they are tightly matched to the trench ecosystem. A delay in locating food could mean losing an opportunity that may not come again for a long time. The pressure also influences how these creatures maintain buoyancy. Fish with swim bladders cannot survive at these depths because the gas-filled sacs cannot withstand collapse. Deep-sea fish instead use oils, lipids, or structural components that do not compress. This allows them to adjust their buoyancy without risking internal failures. Their movements are slow and deliberate because rapid changes in pressure, even within their own bodies, would require too much energy. Everything about their biology is aligned with stability in an environment where stability is the only way to survive. Bioluminescence plays a role, though not in the dramatic ways shown in shallow or mid-depth ocean environments. Down in trench regions, the light produced is faint and localized. It may help an organism communicate with others of its species. It might attract prey in brief flashes. It can also serve as a warning, though the darkness ensures that such warnings are visible only at short distances. The submersible's lights often reveal these small signals for moments before they disappear, giving researchers brief views of how these organisms navigate their world. In some cases, deep-sea animals exhibit transparency. Without exposure to sunlight, there's no need for pigmentation. Transparent bodies help them avoid detection by predators. The lack of colour also reflects the absence of any need to protect themselves from ultraviolet radiation, which never reaches the trench. Their tissues may appear glass-like under artificial light, allowing researchers to see internal structures that would normally be hidden. Transparency helps them blend into their environment, but it also shows how completely their biology has adapted to life without light. Predators exist in these depths too, though their behaviour differs from surface predators. They conserve energy, striking only when necessary. Their sensory systems must detect rare signals from potential prey. Some have large mouths relative to their body size, allowing them to consume prey of various shapes and sizes. This flexibility is important in an environment where food is unpredictable. These predators do not chase prey over long distances. They wait for the right moment, move quickly, and then return to conserving energy. Even microorganisms display adaptations. Bacteria in these depths have cell membranes with structures that resist compression. They continue to function at pressures that would destroy surface microbes. Some thrive in cold, high-pressure environments that might seem uninhabitable. These bacteria contribute to the decomposition of organic material and support the food web. They are a reminder that even the smallest organisms can adapt to extremes that seem impossible. Understanding these adaptations helps explain why exploration is difficult. The creatures of the Japan Trench are shaped entirely by their surroundings. Their biology is matched precisely to the demands of pressure and silence. Anything inserted into their environment must be prepared for those same demands, but machines designed by humans struggle to achieve the same level of compatibility. Where the animals have evolved over countless generations, machines rely on materials that still face limits. The trench forces a comparison between natural adaptation and engineered endurance, and natural adaptation wins in many respects. Exploring these organisms is also challenging because the act of observation can disturb them. Lights may attract or repel them. The movement of a submersible stirs sediment that can alter their behaviour. Some animals rise slightly off the seafloor when disturbed, only to settle again when the water stabilizes. Others retreat into areas where the light cannot reach. Many creatures do not react at all, either because they rely little on vision or because their metabolism is too slow to respond quickly. The Japan Trench contains some species that have never been seen elsewhere. Researchers often discover new organisms during each expedition, but studying them is complicated. Bringing them to the surface is extremely difficult. The pressure differences make survival almost impossible. Many deep-sea animals die during ascent because their bodies cannot adjust to the rapid decrease in pressure. Even when scientists develop specialized pressure-retaining containers, the process is still extremely challenging. Most of the time, researchers must rely on observations made in the trench, rather than physical specimens brought to the surface. The isolation of these organisms gives the trench a distinct character. Life here is not sparse, only hidden and specialized. It continues without reference to sunlight, tides, or seasons. It depends on the slow drift of organic matter, chemical processes in the sediment, and long-term stability rather than rapid and dramatic change. The silence is not truly silence. It is an absence of surface sounds, replaced by the quiet movements of water, the settling of sediment, and sometimes the distant shifts of the earth itself. These creatures demonstrate what life can accomplish under conditions that appear unwelcoming. They reshape the definition of what is possible biologically. Their adaptations highlight the scale of difficulty faced by machines trying to explore the same depths. Machines must resist crushing pressure. These animals do not resist it, they integrate it into their biology. Machines struggle with darkness and navigation. These animals function perfectly without light, and with senses tuned to the conditions around them. Understanding these differences is essential because it explains why exploration of the Japan Trench remains limited. The trench belongs to organisms built for its demands, and every attempt to observe them must account for those demands as well. As exploration continues deeper, the contrast between biological compatibility and technological challenge becomes even more clear, shaping how researchers plan their next steps and how they interpret what they find. The creatures that live in the deepest parts of the ocean are adapted so precisely to their surroundings that their bodies seem almost inseparable from the environment itself. Humans, by contrast, evolved in air, sunlight, and moderate pressure. Our bodies reflect those conditions. Every aspect of our biology assumes a world with breathable atmosphere, consistent gravity, and temperatures that rarely dip below freezing without the help of seasons. This becomes clear the moment you imagine what would happen if a human could somehow descend into the Japan Trench without protection. The outcome would not resemble what happens to deep-sea animals when exposed to pressure changes. It would be immediate and irreversible. There is no gradual adaptation. There is no temporary discomfort followed by adjustment. The body simply cannot function in a place designed for organisms built entirely differently. Pressure is the most obvious obstacle. At the surface, the pressure around you is roughly 1 atmosphere. This is normal, and your body is structured to manage it without effort. Your bones, muscles, lungs, and skin evolved in this environment. When you go underwater, the pressure increases quickly. Divers feel this in their ears because the air in the middle ear must equalize with the surrounding water pressure. Even a shallow dive requires careful adjustment to prevent pain. At greater depths, pressure becomes strong enough to compress air spaces in the lungs and sinuses. This is why divers use equipment that supplies air at a pressure matching the water around them. Without that match, the lungs cannot expand and contract properly. But even this adaptation fails at extreme depths. The deeper you go, the more nitrogen dissolves into the bloodstream when breathing compressed air. At certain depths, nitrogen builds up and causes a narcotic effect. At greater depths, oxygen becomes toxic because high partial pressures cause seizures and organ damage. Gas mixtures can be adjusted, but only to a point. Eventually, the physics of gases makes human breathing impossible. This means that humans cannot reach even a fraction of trench depth while breathing anything, no matter how cleverly mixed. Our lungs depend on gases that behave predictably under moderate pressure. The depths of the Japan Trench exceed the limits of any breathable mixture. Even if breathing were not a concern, the physical structure of the human body collapses under pressure. At 8,000 meters, the pressure is more than 1,000 times that at the surface. This force presses inward on every part of the body because humans rely on air-filled cavities, lungs, sinuses, gastrointestinal spaces. These cavities would compress instantly. The chest would collapse. The ribcage cannot resist that kind of force. The lungs would flatten. The tissues surrounding them would tear. blood vessels would rupture, bones might hold for a brief moment, but the internal pressure of fluids and gases would create destructive imbalances. In reality, the difference between internal structure and external force makes the idea of human exposure to trench depths physically impossible. Deep-sea creatures avoid these problems because they lack air cavities. Fluids do not compress the way gases do. Their internal pressures match their surroundings. Humans cannot achieve this match. Even if one imagined filling the lungs with fluid to remove air pockets, the rest of the body contains tissues and spaces that cannot endure uniform pressure without severe trauma. The brain, for example, is housed in a skull that protects it under normal circumstances, but the fluid around the brain and the brain tissue itself cannot withstand the enormous compressive forces of the deep ocean. The skull would collapse or crack. The spinal column would buckle. No part of the central nervous system is prepared for such conditions. Temperature is another factor. At trench depths, the water is just above freezing. Humans can tolerate cold only with protection, clothing, or external heat sources. Exposure to near-freezing temperatures without insulation leads to hypothermia in minutes. But trench temperatures affect more than comfort. Human cells function within a narrow temperature range. Enzymes slow down when cold. Chemical reactions supporting metabolism become inefficient. Organ systems cannot regulate themselves. Even if pressure were not an issue, the cold alone would stop the body from functioning long before reaching the sea floor. Blood circulation also becomes impossible in such an environment. At extreme pressure, the properties of blood change. The fluid becomes denser. Cell membranes behave differently. Proteins that remain stable at the surface begin to change shape under pressure. This leads to breakdowns in essential functions. Without stable protein structures, nothing in the body can perform correctly. Deep-sea animals possess molecules that prevent protein collapse. Humans do not. The pressure at the Japan Trench would distort human proteins immediately. Even mobility becomes irrelevant because the nervous system cannot transmit signals properly under conditions that alter cell behavior. Potassium and sodium channels in neurons depend on specific pressures and ion balances. These channels would malfunction. Muscles would not receive consistent signals. The heart, which operates through electrical impulses and coordinated muscle contractions, would fail quickly. It cannot maintain its rhythm when the molecular structure of its cells shifts under pressure. Hearing is also disrupted. Human ears contain delicate structures that rely on pressure differences to sense sound. Without the ability to equalize pressure safely, the eardrums would rupture. The inner ear would suffer damage. Balance would be lost entirely. In the dark, cold, pressurized environment of the trench, the body would be overwhelmed by sensory failures long before anything else. Eyes are not suited for the deep ocean either. They depend on light entering through the cornea, travelling through transparent structures and stimulating the retina. In absolute darkness, eyes offer no advantage. Worse, the pressure would deform them. They contain fluid, but the fragile structures inside cannot resist compression the way some deep-sea organisms' eyes can. Photoreceptor cells would fail. The retina could detach. The eyeball itself might collapse or distort to the point of losing any functional shape. The digestive system also depends on gases. Humans swallow air. The stomach and intestines contain varying amounts of gas that help move food and maintain balance. Under trench pressure, these gases would compress violently, tearing tissues and disrupting the entire system. Deep-sea creatures avoid this because their digestion does not rely on gas expansion or contraction. Human skin, though resilient, does not provide meaningful defense against pressure. It cannot protect internal organs from collapse. Even if it remained intact, everything beneath it would suffer catastrophic damage. Blood vessels would flatten, capillaries would burst, the lymphatic system would shut down, the connective tissues holding the organs in place would deform or rupture. There is no path for human physiology to survive such conditions. Even outside of pressure, humans face the problem of isolation. The deep ocean removes every cue we use to orient ourselves. Without light, sound behaves differently. Without breathable air, the body has no internal rhythm to rely on. Without stable temperature, metabolism destabilizes. The environment strips away every reference point. While deep-sea creatures are shaped by these conditions, humans experience them as a complete loss of sensory structure. The body's systems depend on communication with the surrounding environment, light, sound, air pressure, chemical cues, and these cues disappear in the trench. There is also the matter of energy. Humans burn calories rapidly compared to many deep-sea animals. Heart rate, blood flow, body temperature regulation, muscle activity all require energy. In an environment where movement is almost impossible and survival demands total internal consistency, human energy consumption is incompatible. Deep-sea creatures maintain slow metabolisms. They do not waste energy on heat production. Humans, on the other hand, must maintain internal temperature continuously. Without constant energy intake, the body cannot function. The trench does not offer food sources capable of supporting a human metabolism, even if pressure and oxygen needs were not an issue. Adaptation over evolutionary time also plays a role. Deep-sea animals evolved in their environment through countless generations. Each generation selected traits that allowed them to survive pressure, cold, and darkness. Humans evolved in a very different set of conditions. Our ancestors relied on daylight for vision, air for breathing, and moderate pressure for internal structure. These traits worked well for life on the surface, but they do not transfer to trench environments. Evolution does not prepare organisms for conditions they do not encounter. Humans never encountered pressures anywhere near trench depths, so our biology reflects that. Even in controlled environments, the human body reacts strongly to pressure changes. Divers experience decompression sickness if they ascend too quickly. This happens at depths nowhere near the Japan Trench. Dissolved gases form bubbles in the bloodstream and tissues, causing pain, paralysis, or death. Specialized breathing gases can reduce these risks but cannot eliminate them at trench depths. The physics of gas solubility and pressure extremes prevent safe exposure. In a submersible, humans are insulated from these conditions. The hull keeps the interior at 1 atmosphere. Temperature remains controlled. Breathing gas is supplied consistently. But this is not because humans are capable of adapting to the deep. It is because the machine acts as a barrier, protecting the body from an environment it cannot withstand. The submersible is not an extension of human biology. It is a replacement for it at depth. The moment the hull fails, the human body has no defences. This is why deep-sea exploration depends entirely on machines. Humans cannot walk on the seafloor or swim in trench waters. They cannot equalise pressure, breathe, or maintain cellular stability. Every part of human physiology depends on conditions that do not exist in the abyss. The environment shapes what is possible, and the deep ocean makes it clear that biological possibility varies dramatically across different parts of the planet. All of these limitations explain why the Japan Trench remains so difficult to explore directly. Machines can go where humans cannot, but machines must still endure forces that nature designed deep-sea creatures to withstand effortlessly. The gulf between biological adaptation and engineered endurance becomes clear the deeper the descent goes. Each layer of water adds a new level of pressure, cold, and darkness. Humans can only remain present because technology takes the burden. Without that technology, the abyss is immediately fatal. As exploration continues downward, these differences become even more significant, shaping the choices researchers must make about how far they can go and how long they can stay. The deeper the descent goes, the more the environment stops behaving like anything most people would consider familiar. At the surface, physics feels intuitive. You understand how water moves, how light behaves, how sound travels, and how temperature changes. Even pressure at shallow depths is something you can physically sense, and while uncomfortable, it still operates within the boundary of human experience. But as a submersible approaches the depths near the Japan Trench, the physics of the deep ocean begins to assert itself in ways that overturn assumptions. Nothing behaves quite the same. Every law remains the same in principle, but the scale at which those laws operate makes the environment feel almost like another world. Water, for example, becomes a far more demanding medium. At the surface, it flows easily around your hand. It carries sound well enough that you can hear someone swimming nearby. Light travels far enough that you can see the seabed in clear shallows or notice fish passing beneath you. But those perceptions come from circumstances unique to the upper layers. As depth increases, water density rises slightly due to the increasing pressure. This density makes motion harder for machines and changes how energy moves through the environment. The water feels thicker, not because its chemical structure changes, but because the force surrounding it compresses everything within it. When light enters water at the surface, it begins losing energy immediately. Blue wavelengths penetrate farther than others, which is why the ocean looks blue to human eyes. But even blue light doesn't travel deeply enough to reach the depths of the Japan Trench. Long before that point, light becomes so scattered and absorbed that it ceases to function as a tool for orientation. Without sunlight, the environment becomes a space shaped entirely by physics rather than perception. A submersible's artificial lights cut through only a small volume of water before fading abruptly. Engineers understand this and design lighting systems to focus light narrowly, so that energy isn't wasted trying to illuminate an area too broad for the water to reveal. The darkness here is not simply due to the absence of light, but due to the rapid loss of energy as light interacts with particles, water molecules, and microscopic organisms. Sound also changes. Under normal conditions, sound travels faster in water than in air because water molecules are closer together. But in deep-sea environments, the temperature and pressure cause variations in how sound moves. The speed of sound increases with pressure, yet it decreases with lower temperatures. These two factors compete with each other in complex ways. The water in a trench is cold, which slows sound, but it is also dense, which speeds it up. The result is an environment where sound can refract, bend, or bounce unpredictably. This makes sonar interpretation challenging. A ping emitted from the submersible may reflect off a distant object, but the path it takes may curve through layers of water with different densities. The echo that returns is accurate in timing but not always clear in direction, which complicates navigation and mapping. Even the act of movement becomes governed by strict physical limits. Water resistance increases with depth because of pressure-induced density changes. A submersible's thrusters must work harder, pushing against water that resists movement more strongly than shallow water. This resistance affects fuel efficiency, battery consumption, and maneuvering precision. A sharp turn that would be simple near the surface requires more power and time at depth. Every movement must be deliberate. Sudden adjustments risk destabilizing the craft, especially when operating near the trench walls. Temperature adds its own difficulties. Near freezing temperatures slow chemical reactions. Batteries lose efficiency, reducing how long machines can operate. Electronic circuits run at lower speeds. Lubricants inside moving parts thicken. Mechanical stress increases. Engineers compensate for these effects with heating systems, insulation, and specially chosen materials. But every addition increases weight, and weight affects buoyancy. Every adjustment made to counteract one environmental factor influences another. Engineers must manage these competing needs carefully. The deep sea does not offer lenience for miscalculations. Pressure remains the most dominant force in the region. At the surface, the pressure is familiar. At 10 meters depth, the pressure doubles. At 100 meters, it increases tenfold. At 1,000 meters, it becomes 50 times greater. By the time a submersible approaches the trench floor, the pressure outside the hull exceeds 1,000 atmospheres. This is not simply a matter of force pushing downward. It is force pressing from every angle. The hull must resist compression equally in all directions. Any weak point becomes a risk. Even a small deformation can create stress concentrations that grow over time. Inside the submersible, the the pressure remains 1 atmosphere. This difference creates constant strain on the hull. Engineers design vessels using strong elastic materials that can absorb some compression without cracking. But nothing is infinitely strong. Materials that behave predictably on land behave differently under extreme external pressure. Metal compresses slightly, joints shift. The internal shape of the vessel adjusts. These small changes are expected, but they must remain within tolerances. Pressure never pauses. It does not pulse or vary gently. It remains constant and overwhelming, exerting force as long as the vessel stays at depth. Another aspect of deep-sea physics involves buoyancy. At the surface, boats float because they displace water equal to their weight. Submarines rely on ballast systems to control buoyancy. In the deep sea, buoyancy is influenced by pressure's effect on materials. If syntactic foam compresses slightly under pressure, its buoyant force decreases. This change must be accounted for because a drop in buoyancy at depth can complicate ascent. Engineers design flotation materials to resist compression as much as possible, but no material is fully incompressible. Every dive requires calculations predicting how buoyancy will behave. The ability to return to the surface depends on it. The physics of gas behavior plays a crucial role as well. Humans cannot breathe at these depths, but even inside a pressurized vessel, gas must be managed carefully. Temperature changes cause gases to expand or contract. Pressure changes outside the vessel alter the vessel's structural response, which can indirectly influence internal pressure regulation. If internal air cools too much, condensation forms. Moisture can interfere with electronics or cause discomfort for the crew. Heating systems counteract this, but again, heat must be managed to avoid equipment overheating. Everything is interdependent. The chemistry of seawater also shifts under pressure. Carbonate minerals behave differently. Organic compounds break down or interact in ways not seen at the surface. These chemical changes contribute to how sediment forms, how microbial communities function, and how sampling tools must be designed. Collecting a sample at depth means that the sample must be kept pressurized if researchers want to study it accurately. If pressure is released too quickly, chemical structures change. Gases dissolved in the water expand. Particles separate. Even the biological organisms within the sample may die or deform. Maintaining the accuracy of collected data requires understanding how pressure influences chemical reactions. Sediment in the trench forms another physical challenge. Under extreme pressure, sediment layers compact tightly. Yet the top layers remain loose enough to form clouds when disturbed. These suspended particles reflect light and scatter sonar signals. When a submersible moves near the seafloor, it must avoid stirring too much sediment. If visibility drops, navigation becomes even more difficult. Sonar becomes less reliable. Sampling tools may clog. The sediment becomes a reminder that even the simplest parts of the deep ocean behave differently when compressed for thousands of years. Currents in the trench add another layer of complexity. They're not strong by surface standards, but they are steady and unpredictable. Water moves differently in confined spaces. The trench acts like a channel, guiding some currents and disrupting others. Temperature gradients create density differences that push water along slopes. These movements may nudge a submersible slightly off course. Pilots must constantly adjust to maintain stability. Autonomous vehicles must correct their paths based on sensor feedback. A vehicle drifting only a few meters off its intended route may approach terrain it was not designed to handle. Seismic activity adds physical factors that no engineer can completely predict. The Japan Trench region experiences regular tectonic movement. These shifts can alter the topography, disturb sediment, and create vibrations that travel through the water. For machines operating nearby, seismic vibrations can interfere with sensors. Sonar may pick up echoes that resemble obstacles but are actually geological noises. Instruments must distinguish between structural vibration in the submersible and external signals. This adds complexity to data interpretation and requires careful calibration. Electrical conductivity changes at depth as well. Cold, high-pressure seawater conducts electricity efficiently. This increases the risk of short circuits if any part of the vessel or its instruments are not properly sealed. Insulation materials behave differently under pressure. Wires must be protected by multiple layers of shielding. Connectors require designs that resist water intrusion even when subjected to force from all directions. Good engineering reduces these risks, but it cannot eliminate them entirely. The deep sea forces a kind of caution that becomes part of every operational decision. Even simple mechanical actions change under extreme conditions. Opening or closing a sampling device requires force to overcome both water resistance and pressure effects. A latch that moves smoothly at the surface becomes much harder to operate at depth. Robots must use stronger motors. Springs must be selected based on how pressure affects elasticity. Every moving part must endure not only mechanical stress, but pressure-induced changes in material behaviour. Because of these physical realities, time becomes an important factor in missions. The longer a submersible remains at depth, the more pressure affects materials. Even if the hull can withstand prolonged exposure, other components may fatigue. Instruments designed for short-term use may drift from calibration. Lubricants may degrade. Electronics may become less responsive. Engineers specify time limits for each dive not because the machine cannot technically remain longer, but because the risk increases with every additional hour. The deep ocean applies constant stress, and all materials respond eventually. These physical constraints explain why deep-sea exploration happens slowly. There is no way to rush. The environment demands precision. Each step requires understanding the physics shaping it. There is no shortcut around density, pressure, temperature, or darkness. These conditions define what exploration can achieve. They are not obstacles to be overcome permanently. They are fundamental properties of the environment. As pressure increases further into the trench, and the landscape becomes more complex, the physics will continue shaping what explorers can attempt and what they must avoid. Nothing about the journey becomes easier with depth. Everything becomes more demanding. Reaching the deep ocean always comes down to a negotiation between what technology can endure and what the environment allows. Machines have improved steadily over the decades, but each improvement reveals another layer of challenge waiting farther below. The Japan Trench is one of the places where this negotiation becomes most apparent. Explorers bring hardware built from strong metals, engineered plastics, syntactic foams, advanced electronics, and carefully tested seals. Yet the ocean applies pressure, cold, and unpredictability that slowly chip away at human control. Every mission into this region shows that technology has limits, and the trench does not bend those limits to accommodate curiosity. It waits, and it doesn't change its behaviour. The patience of the ocean is different from stillness. It simply continues existing in its own conditions regardless of whether anyone attempts to explore it. Engineering teams build submersibles that can descend to similar depths in other parts of the ocean, but the Japan Trench presents unique complications. The steep and unstable nature of its walls, the unpredictable sediment flows, and the constant tectonic activity all combine to make exploration risky even before the vehicle approaches its deepest points. Machines must be prepared to handle sudden changes. A slope that appears stable may shift. A current may push from a direction that sensors misinterpret. An unexpected vibration may come from distant seismic movement. Technology does not respond automatically to these cues unless programmed or piloted to do so, and even then, the response time matters. A simple example involves propulsion. Thrusters used near the surface operate efficiently, but at trench depths the thick cold water slows everything down. Motors must push harder, drawing more power. Power usage affects battery life, and battery life shapes how long a submersible can safely remain below. If a thruster begins losing efficiency, the pilot loses precision. That lack of precision becomes dangerous when operating near steep edges or rocky ledges. Engineers compensate by using reliable thruster designs and redundant systems, but redundancy only helps when backup components remain fully functional. Cold temperatures, pressure, and constant strain work together to reduce efficiency over time. Communication systems face their own limits. Many deep-sea missions rely on acoustic communication, which can transmit data through the water, but the Japan Trench turns these transmissions into puzzles. Sound waves refract through water layers with different densities, bouncing unpredictably. Messages may distort or arrive with delays. A simple instruction from the support ship may take longer than expected to reach the submersible, and any confirmation from the submersible takes time to return. This delay means operators cannot react instantly to problems. They must anticipate issues before they arise and build safety margins into every decision. Even more challenging is the fact that communication systems sometimes fail completely. Deep trenches interfere with acoustic pathways, rock formations block signals. The length of the descent itself weakens the connection. If a submersible loses communication, the mission cannot continue under normal parameters. It must either ascend or rely on pre-programmed instructions. Autonomous systems help in these moments, but autonomy introduces its own set of limits. An autonomous vehicle can only act based on the environment it is designed to detect and interpret. If something unexpected occurs, the vehicle may not react correctly. This has happened before. AUVs have lost orientation in trench environments. Some have drifted off course and become impossible to retrieve. The risk of losing expensive equipment is more than a financial issue. Many deep-sea vehicles carry instruments that gather rare data. Losing one of these vehicles means losing months or years of preparation, calibration, and planning. Engineers analyze each failure carefully. They examine every recovered component and every piece of transmitted data to understand what went wrong. Sometimes the cause is clear: a damaged seal, a misinterpreted sensor, or an unexpected current. Other times the cause remains unknown because the machine never returns. The Japan Trench has claimed several devices in the past, reinforcing the lesson that technology is not guaranteed to survive here. Material fatigue is one of the more subtle limits. Even if a hull is strong enough to resist pressure, the repeated cycles of compression and decompression stress the material. Over time, microscopic cracks may form. Engineers track usage hours carefully to determine when components must be retired. A hull that has performed dozens of deep dives may no longer be safe for another. Each descent adds strain that does not fully disappear when the vehicle returns to the surface. This slow accumulation of stress reflects the patience of the ocean. The environment does not cause sudden damage unless something goes wrong. Instead, it applies force continuously, allowing no opportunity for the machine to rest or recover. Syntactic foam used for buoyancy also has limits. It is designed to resist compression, but repeated exposure to extreme depth can cause gradual deformation. If the foam loses buoyant force, the vehicle may ascend more slowly or struggle to rise at all. Engineers must calculate how much compression the foam will undergo during each dive and how long it can maintain its integrity. Every additional meter of depth adds risk. The foam cannot repair itself. Once compressed beyond its design tolerance, it cannot return to its original shape. This changes how future missions must be planned. Battery systems illustrate another boundary. Energy storage at the surface benefits from predictable temperatures and easy access to replacement parts. At trench depths, batteries must operate without generating too much heat or losing too much energy to the cold. Some missions use lithium-ion batteries, others use silver-zinc or specialized high-pressure designs, but each option has trade-offs. High-capacity batteries may provide longer missions, but they also generate more heat. Smaller batteries may run cooler but limit how much time the vehicle can remain below. The ocean's patience in this context means that vehicles cannot rely on shortcuts. Energy storage must work reliably for the duration of the dive because there is no opportunity to recharge or replace anything until the vehicle returns. Mechanical arms and sampling devices also face operational limits. The deep ocean turns simple movements into difficult tasks. If a robotic arm closes around a rock or specimen, the water's resistance slows the motion. The arm's joints must resist pressure that tries to force water inward. Even a minor leak can compromise the arm's function completely. Engineers design the arms with heavy-duty seals, but these seals degrade slowly with use. Each dive increases the likelihood that a seal might fail in the future. While maintenance between dives helps, the deep ocean tests components in ways that cannot be replicated perfectly on land. Seals that pass inspection on the surface may behave differently at depth. Another challenge involves the fragile cable connections between external tools and internal systems. These cables must transmit data reliably, power cameras, and control instruments. When subjected to high pressure, cold temperatures and constant movement, the cables stiffen. They may crack if they bend too sharply. They may weaken at connection points where stress concentrates. Every cable represents a potential failure point. Redundancies help reduce the risk, but they cannot remove it entirely. Engineers must strike a balance between outfitting the vehicle with enough tools to be useful and minimizing the number of potential failure points. Mapping the trench requires specialized sonar systems capable of producing accurate readings in an environment where sound behaves unpredictably. High-resolution sonar can reveal detailed images of the seafloor, but only when the reflections return cleanly. In the Japan Trench, seismic activity, uneven terrain, and variable water conditions can distort these reflections. Machines may interpret noise as terrain, or overlook subtle features because the sonar cannot distinguish them clearly. This affects how detailed the maps can be and how confidently explorers can navigate tight spaces. Technology improves each year, but the deep ocean retains control over how much information can be extracted at any given time. Another limit involves the durability of housings for sensitive instruments. Cameras require pressure-resistant casings. Lights need encasements that remain watertight. Temperature sensors and chemical analyzers must operate inside protective shells that keep pressure out and maintain internal stability. These housings must balance strength, weight, and transparency. If they are too thick, they become heavy and distort images. If they are too thin, they cannot resist pressure. Engineers search for materials that provide the right combination, but every material has a threshold. Beyond that threshold, deformation begins, and performance suffers. Robotic systems developed for deep-sea work must also consider how the ocean affects feedback. At the surface, an operator can see exactly what an arm or tool is doing. At depth, delay occurs. Video feeds take longer to transmit. Controls may feel slightly unresponsive because of communication lag. The operator must anticipate how the machine will behave rather than reacting instantly to what it does. For delicate tasks like collecting samples or maneuvering around obstacles, this lag makes precision harder. Technology tries to compensate, but the ocean's conditions force a level of caution that slows down every action. Maintenance schedules must reflect all these limits. A vehicle that performs well during one dive may require extensive servicing before it can descend again. Engineers disassemble parts of the machine, inspect for pressure-induced deformation, replace seals, recalibrate sensors and test electronics. These maintenance routines take time, they delay missions, they require specialized tools and controlled environments. The ocean's patience shows up here too. The trench does not mind waiting. It remains unchanged while people work to prepare for the next dive. Mission planning must account for surface conditions as well. Even if the submersible is ready, the ship above may not be able to deploy it safely because of waves or wind. The water above the trench is often rough. Weather can change quickly. A calm morning can turn into conditions too hazardous for lowering a delicate multi-million-dollar machine into the water. The trench remains where it is, unaffected by the timing, unaffected by human schedules. Technology depends on windows of opportunity. The ocean does not create those windows. It simply allows them when conditions align. All of these limits help explain why the Japan Trench remains so difficult to explore. Technology can only go so far before natural forces dictate what is possible. Pressure, temperature, distance, darkness, and terrain come together to impose clear boundaries. Each boundary can be pushed, but only with considerable effort and risk. No mission takes place without acknowledging how much control the ocean retains. Every success comes from working within the environment rather than trying to overpower it. Machines descend carefully, gather data slowly, operate cautiously, and return with only a fraction of the trench's secrets. The ocean waits. It does not resist intentionally. It does not change to prevent exploration. It simply remains what it is, and technology must adapt around that reality. Every attempt to explore deeper sections of the Japan Trench forces researchers to make choices about what must be risked and what must be preserved. The deeper the descent, the more each decision becomes a calculation about trade-offs. Technology allows access, but access comes with the possibility of losing equipment, data, time, or even the chance to continue exploring. These losses are not dramatic in the way fictional stories depict deep-sea danger. They are practical, incremental, and often slow to reveal themselves. Understanding them shows why efforts to push beyond certain limits remain cautious, and why the trench continues to hold large portions of its landscape out of reach. Loss begins with information. The deeper a submersible travels, the more difficult it becomes to gather clear and consistent data. Sensors that function perfectly at moderate depths become less reliable under higher pressure. Cameras lose effectiveness as visibility shrinks. Sonar systems interpret signals differently when the terrain becomes steep and uneven. Each instrument has a range within which its accuracy remains trustworthy, and beyond that range the readings become harder to interpret. When a submersible moves toward the deepest parts of the trench, these limits accumulate. Instruments drift slightly, or their output becomes noisy. The data collected still has value, but it cannot be analysed with the same confidence. Something might appear as a rock formation in the sonar data, but turn out to be sediment piled in a way the machine misread. Researchers know that pushing too far into these depths increases the chance of misinterpretation. There is also the loss of clarity. Even the most advanced cameras struggle when the light they project reaches only a few meters. The surrounding darkness absorbs illumination quickly. A camera may record a few square meters of seafloor in excellent detail, but everything beyond that looks the same. Black space with no reference points. This means that any footage from the deepest sections of the trench carries gaps. The environment exists beyond those gaps, but the camera cannot show it. When explorers review the footage afterward, they see only fragments, a slope, a cluster of organisms, a patch of sediment. None of these fragments connect smoothly. Without the ability to see farther, the larger context remains missing. This creates limits on how well researchers can understand the relationships between features on the seafloor. Machines themselves face losses in performance. As a dive continues, power drains slowly. Thrusters respond slightly less efficiently. Instruments may cool more than expected, affecting readings. Batteries that start the mission fully charged must be managed carefully, because the vehicle still needs enough energy to ascend and navigate safely back to the surface. If too much power is spent on maneuvering or unexpected adjustments, the remaining capacity becomes a concern. Once the battery reserve reaches a certain level, the mission must end whether or not all planned tasks were completed. This forces researchers to abandon opportunities. They might reach a region worth examining closely, but have to leave early because energy constraints outweigh scientific goals. Another category of loss involves risk to the equipment itself. Every dive wears down seals, joints, cables, and housings. Even if they hold, microscopic stress accumulates. Engineers track this stress and eventually retire components, but when a dive pushes deeper than usual, that wear increases more rapidly. A single mission may require weeks of inspection and refurbishment afterward. This reduces how often the vehicle can be deployed. In some cases, equipment must be replaced entirely. This cost isn't just financial, it also delays future missions, removing opportunities to gather more data before weather changes or funding cycles shift. The deeper the dive, the more extensive the maintenance becomes, and the more time researchers lose preparing for the next descent. There are moments when losses become physical. Some missions have watched as tools failed under pressure. A robotic arm might seize because a seal faltered, a light might crack, a cable might stiffen too much and snap when the vehicle turns. When these breakages occur near the seafloor, the damaged equipment cannot be repaired until the submersible returns to the surface. If a failure affects propulsion or buoyancy, the mission becomes a recovery effort rather than an exploration. There have been cases where deep-sea vehicles lost communication and never resurfaced. The trench simply kept them. These losses emphasize the risks inherent in pushing boundaries. Every piece of equipment that reaches those depths carries a chance of becoming part of the seafloor rather than returning home. There are losses of time as well. Planning a mission requires months of preparation. Teams must coordinate schedules, gather resources, and prepare instruments. Then they travel to the site, navigate weather, and wait for conditions stable enough to deploy. If something goes wrong during the dive, the entire mission may provide only a fraction of the expected data. Even if nothing catastrophic happens, unexpected conditions, currents, sediment clouds, incomplete communication can shorten the duration of useful observations. The time invested in reaching the trench does not guarantee results. This unpredictability contributes to the challenge of obtaining consistent long-term data sets. Pushing too far into unexplored sections introduces another form of loss, the compromise of safety margins. Every vehicle and mission plan includes buffers, thresholds below the maximum limits of the equipment. These margins allow some room for unexpected events. When explorers push deeper or stay longer than intended, they begin to approach those limits. This reduces the safety margin to the point where a small error could become significant. If the ascent takes longer than planned, the battery reserve may reach critical levels. If the submersible approaches a steep slope without clear sonar readings, the risk of collision increases. If the hull experiences more compression cycles than designed, future dives become more uncertain. These losses are not immediate, but they shape future possibilities. The more often limits are tested, the narrower the margin becomes for future exploration. Another loss comes from environmental disturbance. Even the presence of a submersible can alter the surroundings. Lights may disturb animals adapted to darkness. Thrust awash may shift sediment or dislodge organisms. Sampling tools may remove material that took years to accumulate. Each disturbance changes the environment in small ways. Exploring deeper or more frequently increases these disturbances. While researchers take care to minimize impact, exploration always leaves traces. Pushing too far too often means losing some of the natural conditions researchers aim to study. For a region as unexplored as the Japan Trench, preserving those conditions matters because every dive may reveal something new, but only if the environment remains undisturbed. There is also the potential loss of context. Researchers must balance the urge to explore deeper with the need to understand areas already accessible. If missions focus entirely on reaching extreme depths, they may gather less information about regions that lie above. These upper layers also hold valuable data about geological processes, ecological interactions, and environmental changes. Focusing too narrowly on the deepest parts risks losing the broader picture. The trench is not a single point, but a system with layers that influence each other. Ignoring the higher sections to pursue the lowest may limit understanding rather than expand it. Funding can also be lost when projects push too far. Deep-sea exploration is expensive, and each mission must justify its cost. If a project attempts ambitious targets but produces fewer results due to equipment failures, shortened dives, or unexpected setbacks, securing future funding becomes harder. This can halt long-term research programs. When funding decreases, the opportunity to explore the trench diminishes as well. The ocean waits in the same conditions as always, but human ability to study it weakens. These losses are not dramatic, but over time they make a difference in how much we can learn. There are also limits on human endurance. Even though the submersible shields the crew from external conditions, operating at such depths requires concentration and patience. Pilots must monitor multiple instruments, interpret sensor feedback, and adjust controls constantly. Fatigue can influence decisions. Missions often schedule shifts to prevent fatigue, but inside a small pressure-resistant hull, comfort is minimal. Even short dives can become mentally taxing. Trying to push deeper or stay longer than planned increases the chances of human error. A moment of misjudgment can affect the entire mission. This is another quiet loss that comes from extending beyond comfortable limits. Another consideration involves the depth at which submersibles must travel back to the surface after a mission. If problems emerge during ascent, such as unexpected buoyancy issues or communication challenges, the recovery process becomes more complicated. The farther the vehicle travelled downward, the more distance it must cover to reach safety. Every metre upward requires time and power. If ascent begins later than planned, traces of uncertainty accumulate. These are not catastrophic failures, but they represent constraints that influence how far researchers choose to travel. There are times when the environment itself imposes sudden restrictions. Landslides on the seafloor can occur after seismic activity. If one happens during a dive, visibility may disappear instantly. Sediment can overwhelm sensors, interfering with navigation. A submersible in such a situation must retreat carefully. If it pushes too far, the risk of losing orientation grows. This introduces another category of loss, the opportunity cost of what could have been observed. When sediment clouds obscure the area, the chance to document geological events firsthand disappears. Pushing forward despite poor visibility could damage the vehicle. Holding back preserves safety but sacrifices potential discoveries. Ultimately, one of the most significant things lost when pushing too far is the ability to build long-term exploration programs based on reliable, repeated access. If a single mission takes too many risks and results in damaged equipment or incomplete data, future missions may be delayed or reconsidered. A careful, steady approach allows multiple descents over years. An overly ambitious approach may limit efforts to just 1 or 2 attempts. The trench is not a place that tolerates frequent or forceful exploration. It demands patience, just as the machines themselves must accept endurance rather than speed. The deeper the descent into the Japan Trench, the more evident these losses become. They accumulate quietly, they influence decisions subtly, they shape what researchers consider possible. Each step deeper reveals more about the environment, but simultaneously demonstrates why it cannot be approached casually. The challenge is not a dramatic confrontation between technology and nature. It is a gradual understanding that every attempt carries consequences, and knowing where to stop becomes as important as knowing where to explore. Venturing into the Japan Trench always highlights how much remains unknown, not because the ocean hides its secrets deliberately, but because its nature does not encourage discovery on human terms. The environment is stable in ways that seem unchanging, and unpredictable in ways that disrupt every expectation. It does not signal what lies ahead. It does not open paths. It simply sits in conditions shaped by pressure, cold, darkness, and geological processes that unfold on timescales far longer than a single expedition. The mysteries that remain in this trench exist not because researchers have ignored them, but because the conditions required to observe them safely and accurately do not line up with the capabilities of current technology. As a result, the deepest parts of the trench feel less like a place waiting to be explored, and more like one that must be approached slowly, with patience and respect for the limits already encountered. One of the most persistent mysteries involves the shape and behaviour of the seafloor itself. Maps of the trench exist, but they lack fine detail. Sonar provides outlines and depth measurements, yet the complex slopes, cracks, ridges, and sediment layers often remain unclear. Even the best submersible-mounted sonar systems struggle when reflections bounce off steep surfaces. The trench walls curve inward in places, creating angles that confuse signals. The data that returns from these areas looks incomplete or distorted, leaving gaps in the maps. Researchers can infer what might lie behind these gaps, but inference is not confirmation. Each dive fills in small sections, but the full landscape continues to resist straightforward interpretation. Sediment movement adds another layer of uncertainty. Subduction zones such as the Japan Trench experience frequent small shifts in the Earth's crust. Sometimes these shifts disturb the sediment in ways that create long, slow slides. Other times the movement happens suddenly, sending clouds of sediment drifting into deeper regions. Because these movements occur without warning, they can reshape seafloor features between missions. A ridge observed on one expedition may be partially buried by the next. A valley may deepen. A slope that looked stable may shift subtly, changing how currents flow around it. These processes unfold quietly, and because the deep ocean offers no direct cues, they remain mysterious until instruments detect the changes indirectly. Another area of mystery involves life in the trench. Researchers know that organisms exist at extreme depths, but they do not know how many species inhabit the region, or how they interact. Observations during dives reveal only a small portion of the ecosystem. Many animals avoid or ignore artificial light. Some drift in and out of view too quickly to identify. Others remain buried in sediment, emerging only at certain times or under specific conditions. Without direct observation, their behavior remains unknown. Scientists rely on limited samples, but collecting those samples is challenging, because the organisms often cannot survive the ascent. Even when pressure-retaining containers bring samples to the surface, the conditions cannot perfectly replicate the deep environment. Subtle differences alter the organism's behavior, leaving researchers uncertain about which observations reflect natural conditions and which result from the change in environment. Microbial life in the trench offers even greater uncertainty. Sediment samples collected from the seafloor often contain communities of bacteria adapted to pressure and cold. Many of these microbes play crucial roles in breaking down organic material, recycling nutrients, and influencing the chemistry of the trench. But studying them requires maintaining the same pressure that exists in their natural environment. If pressure decreases, their metabolic processes change. They may alter the chemicals they produce or stop functioning entirely. This makes it difficult to study them in laboratories. Researchers use specialized equipment to simulate deep-sea pressure, but no simulation is perfect. Some microbes remain active only under narrow conditions. Their exact roles, interactions, and life cycles remain unclear. These uncertainties form another category of deep-sea mystery, one built not on the inability to observe life, but on the difficulty of keeping that life in a stable state long enough to study it meaningfully. Even the chemistry of the sediment remains partly unknown. The high pressure changes how elements interact, how compounds break down, and how gases behave. Some chemical reactions that occur at the trench floor have no equivalents at the surface. This means that the environment may contain compounds or processes that researchers have not observed in detail. When samples are taken to the surface, pressure reduction alters the chemistry instantly. Gases expand. Minerals change structure. Organic material decomposes differently. These transformations prevent accurate analysis of deep-sea chemistry unless samples are kept under pressure. Because maintaining that pressure throughout retrieval, storage, and analysis is difficult, many chemical processes remain undocumented. Sound is another area with unresolved questions. Researchers know that the deep ocean carries sound efficiently, but the trench creates echo patterns, distortions, and refractions that do not match predictions based on shallow water models. Some noises in the trench come from distant earthquakes. Others come from shifting sediment, underwater landslides, or pressure-driven fractures in rock. A few sounds remain unidentified, not because they suggest anything extraordinary, but because the environment complicates acoustic analysis. The trench amplifies certain frequencies and dampens others. Sounds may appear to come from nearby when they originate kilometres away. Without clear models of how sound behaves in this environment, researchers must work with incomplete data. Another mystery involves the movement of water within the trench. Currents in the deep ocean are slow but consistent. They carry nutrients and particles along the seafloor, shaping how sediment accumulates. But in trench environments, these currents respond to complex topography. Water may move downward along slopes, pool in depressions, or drift upward where density differences create vertical motion. These patterns affect everything from sediment distribution to the movement of microorganisms. Mapping these patterns requires long-term observations, yet the difficulty of maintaining instruments at trench depths limits how much data can be collected. Drifters placed in the water column do not always survive. Some sink too deeply and become stuck. Others move unpredictably due to small shifts in density. Without consistent data, some aspects of water movement remain speculative. There are geological mysteries as well. Subduction zones host some of the most powerful earthquakes on Earth. The Japan Trench is part of a region where tectonic plates meet and collide. These collisions create enormous stress within the Earth's crust. Researchers study seismic activity to understand how strain builds and releases, but many details remain unclear. The deep ocean floor experiences small quakes regularly. Some shift sediment. Others alter the shape of the trench slightly. Because these events occur out of sight, they are detected only by seismometers or by observing changes in the seafloor on later dives. Understanding these patterns requires long-term monitoring, but maintaining equipment in the trench for extended periods is difficult. Pressure-resistant sensors exist, but their batteries eventually run out, their housings degrade, or their communication links fail. Retrieving and replacing them requires missions that depend on favourable surface conditions, which do not always align with scientific schedules. The trench also raises questions about long-term geological processes. Subduction recycles parts of the Earth's crust, pulling rock downward into the mantle. Some of the sediment above the descending plate gets scraped off and forms features in the trench. Some sinks deeper. The exact paths and rates of these movements remain partly unknown. Because the processes unfold over thousands of years, direct observation is not possible. Researchers rely on indirect measurements, modelling, and rare moments when seafloor changes reveal hints of deeper activity. Even with modern tools, much of the underlying process remains hidden beneath layers of rock and sediment far beyond the reach of submersible lights. There are mysteries involving the impact of climate and ocean changes on the trench. The deep ocean does not feel temperature shifts as quickly as surface waters, but long-term changes in the global climate eventually reach even the deepest trenches. How these shifts influence microbial communities, nutrient cycles, or sediment chemistry is not fully understood. Instruments capable of measuring slow changes require long-term deployment, yet deep-sea conditions challenge the longevity of equipment. A single malfunction can remove years of data. These losses slow the pace of understanding, leaving researchers to piece together information from incomplete timelines. Some mysteries involve organisms that have only been observed once or twice. During certain dives, small animals have appeared briefly in the camera's view, only to vanish immediately. The footage offers no clues about their behaviour, diet, or distribution. Without repeated sightings, researchers cannot determine whether these organisms are rare, simply elusive, or part of a population adapted to avoid artificial light. Each rare encounter highlights the possibility that entire species may remain undocumented, living in areas too difficult for machines to approach reliably. Other mysteries arise from the simple fact that the trench has not been explored in its entirety. Many sections remain untouched, not because explorers have avoided them intentionally, but because the terrain makes navigation too risky. Steep slopes, sudden drops, unstable sediment layers, and unpredictable currents create areas where a submersible would need to approach with extreme caution. If conditions change suddenly, retreating may become difficult. Until machines improve, these areas will remain unseen. All these mysteries share a common theme. The deep ocean does not invite exploration. It permits observation only under conditions that technology must respect. When conditions align, researchers gather brief glimpses. When conditions challenge equipment, the trench remains silent. The stillness of the environment is not passive. It is the natural result of physics, geology, and biology operating in ways that do not accommodate rapid discovery. Each unanswered question persists not because the answers are hidden intentionally, but because reaching them requires tools that must operate under demands beyond what most machines can currently manage. The mysteries remain in place while research progresses gradually. Future missions may reveal more, especially as technology improves. But none of these mysteries are likely to disappear quickly. The environment will continue to shape what can be known and what will remain uncertain for some time. The journey upward from the depths of the Japan Trench does not feel like a sudden return. It happens slowly, guided by steady adjustments in buoyancy, careful control of the submersible systems, and constant monitoring of every instrument. The environment changes at a pace too gradual to notice moment by moment, but over time the transition becomes clear. Pressure begins easing, though not in a way anyone inside can sense directly. Temperatures remain cold, but electronics start responding with slightly more efficiency. The darkness remains almost complete for a long while, yet eventually the water begins to reflect light a little differently, as faint hints of suspended particles become more visible. Even so, the ascent remains deliberate because nothing in this environment encourages haste. Inside the vessel, the adjustment feels familiar. Screens display readings shifting inch by inch as depth decreases. The team inside monitors each change carefully. A return from the deepest part of an expedition always feels less tense than the descent, but the crew does not relax entirely. The ocean does not become easier simply because the upward direction leads away from the extreme forces below. Navigation still requires precision. Currents may still interfere with orientation. Instruments continue to send data that must be interpreted correctly to avoid obstacles on the way up. Just as the trench holds its mysteries without intention, the ascent holds its own demands without notice. What becomes clearer during this upward movement is how much the environment shapes understanding. Everything observed during the descent comes from glimpses offered in brief windows of clarity. The trench does not move aside to help exploration. It simply remains as it is, while the submersible gradually loses connection to the absolute darkness and pressure that defined the earlier part of the mission. Each passing meter restores a little more margin for equipment, allowing systems to behave in ways closer to their expected performance. Cameras capture slightly brighter images. Sonar reflections return with fewer distortions. Electronics warm marginally as pressure decreases. These improvements accumulate quietly. As the ascent continues, thoughts often drift back to the work done near the seafloor. The images captured, the samples collected, the sonar maps recorded, all represent new information that adds to long-term efforts to understand the region. Each expedition contributes a small amount to a larger body of knowledge, but the deeper the mission goes, the more obvious it becomes how much remains unknown. The trench's steep walls, sediment clouds, geological activity, and isolated biological communities reveal themselves in fragments. Even though technology improves with each passing year, the environment still restricts the view to narrow beams of light or narrow ranges of sonar. The ascent reflects on that limitation. The submersible rises with data that feels valuable, yet incomplete. In these moments of upward travel, the crew often reviews early recordings of the dive. They study changes in terrain. They mark areas where visibility failed. They note unexpected shapes and movements. The calm and controlled environment of the interior gives time to examine what was captured. Some images show structures whose true size cannot be determined without additional reference points. Some clips reveal animals moving in ways that raise new questions. Others provide clear views of sediment layers or rock formations shaped by geological processes that continue far below human observation. Each piece becomes a starting point for future planning rather than a final answer. The crew might discuss what went as expected and what did not. If a current pushed the submersible slightly off course, that detail becomes important for the next mission. If a robotic arm resisted movement because of pressure, engineers will investigate. If acoustic communication broke briefly, the team will record the conditions that may have caused it. The ocean does not explain these events, so it is up to the researchers to make sense of them. The ascent becomes a time for organising these thoughts while still respecting the environment around them. Closer to the mid-depths, the water remains dark, but not in the same complete way found near the trench floor. Small particles drift through the beam of the submersible's lights more clearly. The water no longer carries the same heavy stillness. There are subtle signs that life becomes more varied here. Occasional silhouettes pass near the lights, not numerous or crowded, but more frequent than in the depths below. The presence of different species reminds the team that the ecosystem changes with depth, creating transitions that reflect shifts in food availability, temperature, and metabolic demands. These layers form part of the larger ocean system that connects even the deepest trench to the surface. The upward movement continues at a controlled pace, because sudden changes in positional speed could interfere with navigation. The submersible must avoid any rising sediment or unexpected formations. Even though the environment grows gradually less demanding, the team cannot assume that conditions will remain stable. The ocean's ability to change without notice is not limited to the deepest areas. Currents might push the vessel sideways. A shift in water density might alter buoyancy slightly. The temperature may fluctuate as the vehicle rises through different layers. Each adjustment requires monitoring. During these stages, communication with the support ship becomes clearer. The acoustic signals experience fewer distortions. Messages travel more reliably. The delay shortens. This improvement helps the team coordinate with the surface more comfortably. Instructions can be exchanged without the same level of caution required at greater depth. This communication often includes early reports of what was observed, requests for surface teams to prepare equipment for retrieval, and updates on remaining battery levels. The ascent itself becomes a form of preparation for the work that will take place once the submersible reaches the ship. As the submersible rises further, light from the surface remains far out of reach, yet the sense of being closer to familiar conditions becomes noticeable. The pressure outside the hull continues dropping, at a rate that allows both the machine and the crew to adjust comfortably. The vessel's systems begin functioning in ranges closer to their natural operational limits. Heating systems require less energy. Thrusters respond more predictably. Sensors stabilize. These shifts do not happen suddenly, but the crew can tell when the environment begins to resemble depths that have been visited many times before. During this time, reflections often turn toward the larger purpose of the expedition. Each dive into the trench continues a long history of attempts to understand parts of the planet that do not reveal themselves easily. The seafloor captured in the cameras may show things never seen before. A sample collected from a trench wall might contain microorganisms adapted to pressures and temperatures that challenge laboratory study. A map created from sonar readings might reveal a new slope or ridge. These pieces fit into ongoing scientific efforts. None of them answers every question, but each one provides a starting point for future dives and future analysis. The further the submersible ascends, the more the equipment gradually shifts from defensive mode to routine operation. Engineers on board or monitoring from the ship prepare for the end of the mission. They consider which instruments require detailed inspection afterward. They determine which seals need testing, which electronics need recalibration, and which components may require replacement. The trench's influence does not end when the submersible leaves it. Pressure cycles, temperature stress, and mechanical strain all remain part of the machine until it is serviced. The crew knows that the next mission depends on how well they address these needs after reaching the surface. Farther up, the water column becomes more dynamic. While still dark, it contains more movement. The submersible begins encountering occasional changes in current direction. These currents do not resemble the turbulence of shallow waters, but they remind the crew that the ocean is not uniform even at moderate depths. Adjustments remain necessary. Each movement of the vessel must maintain stability. Thrusters correct gentle drifts with small bursts of power. The crew continues monitoring fuel levels and energy reserves, ensuring that enough remains for final maneuvers near the surface. Eventually, the ascent reaches depths where faint light from above can be detected through sensitive cameras, even if the human eye cannot see it yet. The water shows a slight change in clarity. The beam of the submersible's lights reflects differently. It becomes easier to distinguish objects at a distance. These subtle transitions indicate the approach toward layers where sunlight begins to play a role, even if only in minimal amounts. The shift does not provide visibility in the way divers experience at shallow depths, but it marks the gradual reconnection to the part of the ocean where conditions begin to resemble the world above. As the vessel continues rising, discussion often turns to how the dive will be presented once the mission is complete. Researchers consider how to organize the data, which findings require further analysis, and which questions emerged unexpectedly. The work that follows the dive can take months or years. Samples must be tested, maps must be refined, observations must be compared with previous missions. Every expedition adds to a chain of knowledge that stretches back across decades. The trench offers glimpses, and each glimpse becomes part of a long-term effort to understand how the deep ocean fits into Earth's broader systems. The ascent continues until the first signs of natural light finally reach the outer hull. At this point, the environment changes more noticeably. The darkness begins to fade from absolute to partial. Cameras start capturing details without relying entirely on artificial illumination. The pressure, though still far greater than at the surface, no longer threatens the structural limits of the hull. Thrusters work more efficiently. Communication with the ship becomes consistent. The crew prepares for the final phase of ascent, which involves navigating the distance between mid-depth waters and the surface layers where waves and wind begin to influence movement again. As the submersible approaches shallower depths, the water grows brighter and more dynamic. Marine life becomes more abundant. Schools of fish may pass nearby. The transition from stillness to movement becomes clear. The environment feels less isolating. The ascent slows slightly to accommodate the changing conditions. Instruments continue recording data until the team confirms that all essential tasks are complete. The final steps involve coordinating with the support ship for retrieval, ensuring that the submersible surfaces in a controlled manner and preparing to secure it against the motion of the waves. When the submersible finally breaks through the surface, the contrast between the trench and the world above becomes immediate. The crew sees the sky again. They feel the movement of the air. The sound of the ocean changes from the steady hum of deep currents to the familiar rhythm of waves and wind. The environment that shaped the entire mission remains far below, unchanged and unaltered by the presence of the vessel. The trench retains its depth, its pressure, its silence, and its hidden terrain. The submersible returns not with a sense of completion, but with material to study, questions to revisit, and new clues that point toward future efforts. The return to the ship brings a different kind of work. Equipment must be inspected carefully. Data must be transferred, backed up, and reviewed. The hull must be checked for signs of stress. Tools must be cleaned and prepared for analysis. The team discusses what went well, what requires improvement, and what they might attempt on the next mission. The transition from deep-sea environment to surface routine is gradual and methodical, just like the rest of the expedition. Later, when the footage is reviewed, the images collected at the trench floor feel distant but valuable. The scenes captured by the lights show landscapes untouched by sunlight, shaped by forces that operate far beyond human presence. The organisms recorded reflect lives that follow rules unfamiliar to surface biology. The geological formations show slow processes that continue regardless of observation. These images remind viewers how different the deep world is and how much remains unexplored. And as the narration reaches this point, drifting upward with the vessel, the listener is invited to come back toward the environment they know, one with daylight, breathable air, and familiar surroundings. The deep ocean retains its mysteries far below, but the experience of travelling through these ideas remains with whoever has followed the story to this moment. Before we fully return, it's a good moment to ask where you've been listening from, whether you're ending your day or still wide awake somewhere in the middle of it. If spending this time together felt calming or interesting, you're welcome to stay connected by liking, subscribing, or returning for the next story. There will always be more to explore, more questions to follow, and more quiet journeys to take. And now, as we rise back toward the light you're used to, we simply continue forward, carrying everything learned from the depths without needing to say goodbye to the place we've just left.